environmentally harmless products, right? And for this, you need real-time analysis to prevent pollution, something not just when you maybe look at when you dispose your product and then look in the long run, but you need to look at this over the whole process. And then, as I already said, minimize potential for accidents is something I find also very important, has improved a lot. If you look over the history, fortunately, if you look at major chemical accidents, let's say in chemical companies, plants or so, fortunately, there are very little if you consider how much chemistry is being done. And so I believe that it's, again, a major accomplishment that chemical processes has been made safer and safer over the last years. So let's look at some of these things you said, like operational efficiency. And so I'm just showing some ideas in here. So if you look at an industrial process and you would like to run a reaction, what do you think is the least desirable, not the best, but what do you think is careful here, the least desirable temperatures to carry out a reaction? And so I just give you some ideas here. And I can see that you guys have very different ideas about this. And you can also see that you can correct answers and take back answers and all these issues. Okay, so I'm not completely sure, maybe the question, if it was phrased okay. So you guys don't like the high temperature in the as a process. We will see many industrial processes which run at such high temperatures. And in fact, the high temperatures very often are not so much a problem. It's energy intensive, it's no question about this, but it can be handled very well. And very often high temperatures, but then the reaction times become very short, are very efficient, and even from an energy point of view. And so high temperatures, I put down 500 degrees, 200 degrees, 100 degrees. That is typically not so bad if it is run efficiently. Ideally, you would like to see a reaction at room temperature, right? Because that is what we have around. So room temperature in Germany is 20 degrees. Room temperature in India is 35 degrees. So not so easy to define this. And but the one thing which is really critical and industry hates and is hardly doing are low temperatures. So 0 degrees might still be okay. You can do with ice cooling or some cryos. Minus 20 degrees might still be okay. But anything you need to go below this becomes difficult, and it becomes energy intensive because you need to make the low temperature. But there are other problems with this. So there are problems with that you start forming ice everywhere, right? If you run a reaction in your lab, you do a reaction at low temperature, you start forming ice everywhere. You condense water into your reaction flask very easily. So low temperatures are much less desirable, minus degrees temperatures, than high temperatures. Okay, so I'm not sure if you're old enough, but you said safer chemistry, less hazardous way. Do you know any type of typical chemistry which is more efficient today than, I think, on your time perspective, probably 10 years ago, my time perspective 30 years ago, which became much better to do? And as I said, no answers here, so that's probably because you are too young. You don't know the differences. Okay, so the Wittig reaction, we will talk about the Wittig reaction today in the tutorial. I'm not sure if it has changed. It's still more or less the other thing. So two persons of you mentioned photochemistry. This is something, again, if you are old enough like me, you would completely agree. And we will talk. We will have a whole day on photochemistry and photocatalysis. Photochemistry is a relatively old technology. It was done in the 60s. It was done in the 70s. But one of the big differences was that it had used these high intensity mercury lamps, which generated a lot of heat. And so when I did a photoreaction in my PhD, which I did, which we would do with these high pressure mercury lamp or medium pressure mercury lamps, which generated a lot of heat, we had to make sure that the cooling would work, and we would have to make sure that the cooling would not stop. So for some reason, the water cooling would keep flowing. There's no tube would go, would maybe break, or there would be a water shortage. So if I would like to run a reaction overnight, this would mean I would have to stay in the lab to make sure that everything is okay. I could not dare to go home, because then if something would go wrong with the cooling, this whole thing would probably explode. And so this, and I think this is one of the major driving forces of photochemistry today. Now we have LEDs, which which generate a lot less heat, depending on the wattage. It still might generate quite a bit of heat, but we can just shine an LED from the outside of a flask or from some plate we use, and that has become much safer and much easier to operate. And I think this is one of the issues we have now, that chemistry became much more applicable in operationally synthesis. Electrochemistry, electrocatalysis, I'm not so sure. We will talk about this as well for one whole lecture. I think there we have what has made it more easily to operate is that we can now buy kits, the whole reaction setups, which you can just start using. But we would do this 30 years ago in the same way. We just had to build it ourselves. So I'm not completely sure if this was a driving force, or if the whole principle of one electron chemistry, which we will discuss in photochemistry but also in electrochemistry, if this really was a driving force. Okay. So let me, in order that we are not going on too things, I need to make sure that we are not running too much over the time. So let's start with the atom economy. This is something you guys like very much. So name a reaction which has little or no waste. This was what people like Barry chose. He started to emphasize this with the term atom economy. But then there was also people like Barry Sharpless, Nobel Prize winner, a twofold Nobel Prize winner, who emphasized the idea that reactions which can be in a way addition type reactions have little or no waste at all. So somebody says the Aldo reaction. It's an interesting question, because in an Aldo reaction, that might be maybe atom economic, because if you add an enolate with an aldehyde, that's a net addition reaction. You need to make the enolate, right? And so for the enolate, we are using base, and very often we are using base in a non-aqueous environment. So typically LDA, right? Lithium diisopropylamide, or maybe even butyl lithium. And so then we are starting massively making lithium salts as waste, probably more than the reactants which we have, right? So addition reactions, cycloadditions, that's a pretty good idea, right? So somebody wrote also the Diels-Alder reaction. That's a typical prototype of a reaction. Hydrogenation of alkenes, that's also very, very important. And Michael addition. So you see already the idea. All types of additions is typically a very good way. I need to see what I need to do if I want to, if I want to use the pen, cannot use it, right? What do I need to do in order to switch back to the pen now? Okay. Okay, now here it is. Okay, then I can do it. It just didn't didn't show up on the slide, right? So you said addition reactions, and if you, like the Diels-Alder reaction and so on, if you look from an industrial point of view, indeed the one reaction we are using probably almost, and if you at least talk about catalysis, almost using the most, are indeed hydrogenation reactions. So let me see if this works now. So if you have obviously, if you add hydrogen across a double bond and the alkenes, you typically will get somehow from fossil fuels, from oil. But then the other reaction, which is really done on tremendous scale, oh, gee. Okay, so let's see again if I need to switch this. So pan. So the other reaction, which is very related, which is done in industry a lot, is the hydroformylation, right? Addition of hydrogen and carbon monoxide and this will generate aldehydes, right? And so both of these reactions, the hydrogenation, where you get the alkenes from the fossil fuels, but also in order to make functional molecules out of this, the hydroformylation is a very important reaction. And both of these are catalyzed reactions, right? So typically we can use many precious metals, palladium or not so precious metal, nickel. The hydroformylation is typically done by cobalt or rhodium catalysts, which is been done. And again, we are talking here reactions which are done on million-ton scale. We are not talking small reactions, right? Reactions like the Diels-Alder reaction, indeed, dream-type reaction, addition reaction, that is, from an industrial point of view, probably a lot less being applied. So now if we look at, so let's look at the concept you guys all like so much. This is the concept of atom economy being pioneered by Barry Trost in 1991. Barry Trost, still a professor at Stanford University, very impressive CV. If you heard about CVs, I tell you what an impressive CV is. Who of you is already 24 or older in this auditorium? Okay, so I'm shy. Barry Trost, at the age of 24, became an assistant professor at University of Wisconsin. So he had already finished the PhD. He was so brilliant that he didn't need a postdoc. They made him a professor right away. And I think at the age of 30, he was a full professor and has done, he is now in the middle of the 70s, I believe, has done numerous contributions and has always been up for the Nobel Prize in chemistry. And so he coined the term atom economy. And with atom economy, he was defining this. What is the molecular weight which is in the product compared to the molecular weight in the reactants, right? And so with this type of definition, an addition reaction, like a hydrogenation, is 100% atom economic, because your alkene and your hydrogen, these are your two reactants, everything goes into the product, right? And so you have a percentage of how many reactive atoms remain in the target product. And you can have this, you can calculate this as a single reaction or as a whole, a series of reactions, and you can look at this, right? And so this was his definition. And now let's look at an example, which is not 100%. And so that's the biological photosynthesis, right? And in that biological photosynthesis, you react carbon dioxide with water, and that is done by the sunlight, and you have a catalyst, which is chlorophyll. And with this, you're getting out sugars, and then you get 6 molecules of oxygen. And so if you would look at the from an organic synthesis point of view, if you would look at the product formation, then the sugars here would be your product, right? And if you now calculate the atom economy, then you would have 6 molecules of carbon dioxide, so that's the molecular weight here, 6 molecules of water, and so this gives you the net sum of your starting materials, and then you would have the product, which is here your sugar is 180, and if you divide 180 by 372, you come to an atom economy of 48%. That's not very high, right? And there's waste apparently produced. But look at this, at least, and that's why I said we need to be careful what we define as waste. The waste is oxygen, and this allows us to breathe. Without this waste, we could not live on Earth, right? And so atom economy might be, from the organic synthesis standpoint of view, might be very, very low, but maybe the byproducts you might form are very useful. And you will see that this is a strategy which is done in industry a lot, and especially in companies, big companies like BASF in Germany, who can do everything, who are not doing just one process, who are doing hundreds of different processes, and very often they are able to do something very useful with what we call waste is being produced. Okay. So there is also the atom economy concept, which was introduced by Barry Scholes in 1991. After this, a lot of other factors were defined because people said, well, maybe atom economy is not the only good measurement we should use. And very importantly, there's something like an E factor, which was introduced. There's something which is called reaction mass efficiency, process mass intensity. I give you a short idea of all of these type of parameters, and then we can look at this. Okay, so we don't need to do this. We have already named a number of reactions with perfect atom economy. So let's skip this. And so again, this is another example for an atom economy. So if you consider like an esterification of this carboxylic acid with methanol catalyzed by an acid, you form the methyl ester in water. You probably have even done such a reaction in your laboratory, experiments and lab courses. If you calculate the atom economy, it's actually pretty good, right? It's 87% because this is your product and these are your starting materials, and so you can do it yourself. You find out what it is, and the byproduct is actually pretty benign, right? Because the byproduct is only water. So people pointed out very early that there are limitations to this atom economy type concept, and one of the limitations is you consider only the reactants, like the two things which are being used here, but you're not considering solvents or reagents, right? So we need a reagent here, paratolusulfonic acid. We have not really said how much we need. Principle, it's a catalyst. We need a solvent, which is probably also pretty good here because the solvent is probably methanol. We are also not considering the stoichiometry. So a reaction might be very atom economic, but you might have to use one of the reagents in a large excess. But that is not considered in the concept of the atom economy, right? And so therefore, it's the reaction yield. If you take into account excess of reagents, that's not really considered. And we already said that if you have so-called waste products, but which are benign or which are beneficial, this is also not being considered. And so therefore, people have used other metrics. I just give you here a number of reactions which in the concept of Barry Scholes are very atom economic. We already said additions are very good because they are 100% quantitative. Condensations are probably pretty good. We just looked at the esterifications, and there you typically just generate water, so very little waste, small molecule, but also a benign molecule. But then there are other reactions like eliminations, right, where you need stoichiometric bases. They become not very atom economic any longer, and And so obviously everybody has seen this. Additions are great. Eliminations, the reversal of this, are typically not very atom economic. Okay, so we had the limitations. And so then people were looking into parameters saying mass efficiency, where they say, well, we look at the mass of the products, and then we look at the mass of the reactants. And the reactants, now in this type of measure, you take into account that you might use an excess of a reagent, right? And so you filter this in, that your total mass here, so this is your product, and then you divide it by the total mass you employed, and here you consider the excess you have also employed, right? So you can see then suddenly the reaction mass efficiency typically is lower if you have to use anything in excess than the atom economy, right? And so there people felt that this is something you need to take into account as well. And just to give you, let me just skip this, and then there's something which is the E factor, and that is probably the most useful. This is probably the most useful type of definition. This came 3 years later. This came from Sheldon, who's one of the really pioneers of green chemistry and who have thought a lot about green chemistry. And he said the E factor is the mass of the total waste to the mass of the product. And now this suddenly considers everything, right? It takes into account all the type of waste you might have. And I give you just here an example, a simple elimination of a Hoffman elimination where you isolate an amine and then do the elimination, and this would be your product. But then you can see this is being done with methyl iodide, which is not really in the product. You need silver oxide as the base to do this, and then you see you form a lot of different types of byproducts. And then if you calculate the E factor, then you see here, which comes out 12.9. This means that for 1 kilogram of product, you're generating 12.9 kilograms of waste. And that is now suddenly a reaction which might be considered more or less atom economic, becomes suddenly a much more problem. You can see that in this example, the solvent is not incorporated in this as well. And if you look at some of the, I go back now, if you look at some of the industrial processes which have been done in industry at a way, this was a process which was done 70 years ago, the synthesis of fluoroglucinol, which was done on 100 tons a year. You can see this is this 1,2,3,5 trihydroxyphenol. This is a reaction which people started from TNT, trinitrotoluene, which you probably know better as an explosive. And in a 3-step process, which involved heavily oxidation chemistry and substitution chemistry, they've been able to convert this into this phenol. And the yield of that 3-step process is better than 90%. So from a yield point of view, it's fantastic. But from an economic point of view, it's a disaster, because you can see they're using chromium reagents like crazy. And so they were producing around 40 kilograms of chromium-containing waste per kilogram fluoroglucinol. So the E factor would be 40 here, so that's very bad. So although the yield was fantastic, the atom economy and also the E factor simply was a disaster. And here's another example which I think is also pretty much in everybody's mind, that stoichiometric reactions are typically less effective than catalytic reactions. And let's look again at a famous example, and this is the reduction of nitrobenzene to aniline. This is a reaction which is again done on millions of tons, and a company like BASF. I don't know if you know what the A in BASF stands for. Does anyone know? I didn't put this as a question. Does anyone know what the A in BASF is? You all know about BASF because you have BASF in India. There's a big plant in Mumbai. Right? The A stands for aniline, this compound here. because the big process BASF became big in, and actually even a previous company before, was exactly this reaction, the reduction of nitrobenzene to aniline. And from aniline, you could make dyes. And that is how it really started. Like all the dyes, all the color dyes you have in your clothes, this is actually coming back to aniline at some point. And in order to make aniline, you would take benzene and do a nitration to make nitrobenzene. And so the BASF found this company found that process so important that they put the A into its name. The S stands for soda. That's sodium carbonate. This was the other big process they've been making. Okay, and then this is the traditional process how you would do the reduction. You would do it with iron. That's a pretty great reagent, right? Because we have iron is the most abundant transition metal on the planet. And so they would do the reduction with iron and as a catalyst, and iron salt, iron chloride. And so the iron would reduce the nitro compound to the aniline and itself gets oxidized, right? And you can look at the atom economy. Again, I give you the numbers here and you could calculate this. The atom economy is not very, very high. The yield was great, and of course iron was very inexpensive. You can do this catalytically, and if you do this catalytically, you can use a nickel catalyst, which also is already very good. So it's not palladium or platinum or rhodium. It's also a metal which is quite abundant, not as abundant as iron. You can do hydrogen, and so if you do this reaction, you get aniline, and you have a much better atom economy, because as a byproduct, you're only making water. You see here as a byproduct, you're making iron oxide, rust. The interesting question is, if you compare this, it's not really clear what is better, because you can run this first process at much lower temperature. And you see here, you need 300 degrees. So that's what we talked about earlier, about high temperature, right? High temperature, and you need pressure. That's another factor. If you do a reaction under pressure, it's a safety issue, but industry is very good to do reactions with carbon monoxide or hydrogen under pressure, right? And so here you can see, if you calculate the atom economy, that's much better. You have not really taken into account the energy you need to use in order to do this type of process. Okay, and so then we talked about safety. And that is another thing which I also will talk with you a little bit more later during the course, that reactions became much safer. And that is a pretty good example here, where people have done the reaction in flow, so where you bring the reagents, you introduce them into your reactor. But also, you see, this is the reduction here of nitronaphthalene to aniline. You see what they're doing here is, you have in the one tube, you bring in your nitronaphthalene, but then in the other one you need hydrogen. But the hydrogen you're producing in situ. That again makes it much safer. You don't need to bring in your big hydrogen tank and pressure the hydrogen on and all this right away. They're using water here and then electrolysis, and so they're generating always as much of the hydrogen they just need in the moment to do the reduction. And so then this is being in a flow reactor brought together. It is being pumped through a reactor which contains the catalyst. You see here it's palladium on an aluminum oxide support. And then this way you are getting out the product. And so again, this makes this type of chemistry much safer, and you can also run it in a much smaller reactor and just doing a continuously pumping in your reagents into the reactor and then getting it out of the reactor as well. Okay, so we talked about the E factor, and as I said, this is the mass of total waste to mass of product. And it's one of the limitations is it's not considering recycling. And that's of course another important issue, that if you make waste or whatever byproducts, if you can recycle it, that might become very different how you evaluate a process. And today, later in the tutorial this afternoon, I would like to discuss with you a process where you would probably say immediately, we will compare two processes, and you will probably say immediately the one is much better than the other one. But if you look more carefully into this, and especially the idea of recycling, it might be different. It might be a different way. And also solvent recycling is a very important issue, and which might also make you consider things differently. And so when we talked about the green principles in the beginning, some of you said greener solvents. And the question is, what is a green solvent? And I think most of the people you ask, they will say it's water, because we have a lot of water, and it's abundant, and it's non-toxic. We all know we can drink it, and so on. But if you have ever done a reaction and tried to recycle water, it's typically a nightmare, right? If you want to distill water out of your reaction mixture, it's not working very well. And nevertheless, that water you use for a reaction is still being contaminated. You would not like to drink the water after you have done the reaction with this, right? You would know that there are contaminations in there. And so redistillation is very difficult, but also burning is very difficult, right? Sometimes you can burn a solvent, use the energy we get out of this. You cannot do this with water, because that's one good thing. It's non-flammable, but on the other hand, it produces indeed waste, contaminated waste, which you also need to, it's very different to upgrade again, right? And so that's what you need to do. And so also the one thing which the E factor also does not really take into account is what you need to do afterwards in the workup, right? You very often need to neutralize a reaction, then you need to do extractions with water or whatever. That's not in there. And the one thing we also discussed already is it's not taking in the energy you need for a process. Okay, so here again there are more ideas on the same reactions on the E factor, and you can see that the E factors can vary quite a bit. If you just look at reagents, that E factor would be this. But then if you take in the solvent, then the E factor goes up quite a bit. And then if you take in the water you use for producing, but also maybe for extracting and workup, then the E factor, you can see, becomes very, very different. So very often people might, depending what you would like to push, and emphasize the reaction in saying it has very little, it has an acceptable E factor if you just look at the reaction. But all things considered, solvent, water you need for extraction, and so on, it might be a very different one. I see some people making pictures. This is all okay. You can make as many pictures as you want, but the handouts are available. So all the slides you see here, I'm not sure how Sangeeta is doing. Sangeeta is in charge of the technical issues here. All the handouts are on WhatsApp, or I don't know where you put it, but as I say, I have no problem. You can make as many pictures as you want, but you don't need to, because we are giving you all the handouts. Okay, and so then people have made nice pictures and diagrams for this in order to visualize the different impacts. And that's something which they call this process mass intensity. So the total mass in the process step, where you need everything, solvents and so on, divided by the mass of the product. And then you can make these nice graphs here. And then you can see that very often the most critical issue is the solvent which goes in there. And that's one of the things where you can make a process very often a lot greener if you're able to use little or maybe even no solvent, right? And then the other issue very often is the water you need to do an extraction for your chemistry. And then reactants might be, and other issues also might be a much smaller issue here. Okay, so then the question, how can you increase energy efficiency of a reaction? And that is something I think we have maybe also, I don't know if you have an idea to this or not. We covered some of the issues already. Not sure if something comes up here. So one of the big issues which we are going to talk about is indeed catalysis, right? So that is a way to lower activation barriers and make reactions more energy efficient. And so let's stick with this. This is something which we are going to look at, right? And so here are some more examples, and it's, I think, very obvious that catalytic reactions are much better than stoichiometric reactions. Again, here's the typical Jones reaction you might do in a lab, which oxidizes an alcohol to a ketone, and it makes chromium waste. That's, of course, very bad. So you have a bad E factor and also a bad atom economy because you're making these chromium salts. But then if you do the same thing with a catalyst and oxygen, that's, of course, the most benign oxidant you can think about, then the atom economy becomes very good, the waste becomes very good. But again, this is something which requires temperature. And so again, and one of the things to make this more energy efficient is to develop better catalysts which can do reactions then at lower temperatures, right? Okay, so we talked about this. Let me just give you an idea today what people think is acceptable for these E factors. So, right, so E factor is the kilogram waste divided by the kilograms of product. And typically, if you start from fossil fuels, oil refining, that is something you do in tons per year, like 1 million to maybe 100 million tons per year. There, the E factor obviously have to be very low, right? And typically they are in the order of less than 0.1 kilograms. So oil cracking, for example, the idea to make from larger hydrocarbons, make smaller hydrocarbons, this is more or less a reaction. Let me see if I get the pen. So typically what we do in oil refining, right? Let me remind you. Okay, I try this again. What we are doing, right? So in oil refining, we typically we have hydrocarbons. So let's take an octane. And then what we do is by applying heat, we can crack this into smaller parts, right? Because under the heat, we start breaking the carbon-carbon bonds. And so once we form such radicals, we will talk a lot about radical chemistry. If this now takes one hydrogen from here to here, then you form a new alkane, and in this case you're forming ethylene, right? This is one of the ways we do the oil refining and making smaller type of hydrocarbons which we can use for chemistry. Again, this has essentially an E factor of close to 0, right? Because there's no waste. And the downside is that the reaction temperatures you need here are again very high, right? It's a very energy intensive process, and in order to do this, but from a waste point of view, it's a very efficient process. And then you can see there are the other things like biochemicals, typically things which we produce in larger quantities, but not on this million-ton scale. Their E factors are acceptable, in the range of 1 to 5. But think about this. If you have 5 kilograms waste for 1 kilogram product, that is still a lot, right? That is something you would like to have much, much lower. And then fine chemicals, essentially fine chemicals, everything you can buy from Aldrich, more specialized chemicals already. The E factors, you see, the smaller the amount you produce is, the larger the E factors could become acceptable. And if you make drugs, pharmaceuticals, that is something you typically only do on, typically very often even below a ton scale. Then E factors can become very, very high, because now we are talking about very specialized chemistry. But there you can see is that with modern methods and organic synthesis, there might be a lot of improvement possible here. I will want to talk to you today during the tutorial. I would like to discuss with you the vitamin A synthesis. And vitamin A is a compound which probably just every big chemical company has a process for. And I want to discuss with you this afternoon, I want to discuss with you the BASF process, because this is something I believe one can learn a lot, how you can do a process which looks inefficient, which we can become very, very efficient, right? In the vitamin A synthesis, people typically, they needed these type of ketones. If that gets dimerized, this makes the vitamin A, and vitamin A, beta-carotene, is a vitamin we all know and we take as supplements, which is being added to animal food and so on. So that is something which is being done on very large scale. BASF, to give you an idea, is making 3,800 tons a year of this. And you can see this is not just oil refining any longer. This is already pretty sophisticated synthesis. You see here the chemistry of organon. You see how old this is, 1946. Even I was not born at this time, right? So, and you can see what people have done. And if you look through this, we can look at a few steps and just make some general terms how efficient or how green we would think that this type of reactions is. They all start from this, all the syntheses from the company start from this molecule here, iononine, and I show you how this has been done by BASF, and I think that's, again, pretty spectacular how this can be done. But let's say that is our starting material. So the organon synthesis, they start adding of this pre-functionalized starting material, and they're making essentially a grignard. But they're not making the grignard with magnesium. That is what you usually would do. They're making the grignard with zinc. That's already a pretty interesting choice, because zinc is very non-toxic, and it's also widely available, as is magnesium. And it is it's very selective. You see, you have here a reaction where a nucleophile could attack multiple positions, and so they're making the zinc analogous grignard reagent, and they're adding it to the carbonyl group here. And you can see something else. They're using a solvent you would not use today any longer, right? We all know that benzene is carcinogenic. At that time, people would wash their hands with benzene, like sometimes, again, and I must caution you, sometimes we do this with acetone, right? Now we have in the lab for cleaning labware, we have acetone. In these days, they cleaned the lab gear with benzene. And they thought that is all great. And we think today acetone is great, it's very harmless. And in nail polishers, sometimes you have acetone. You need to be careful with acetone as well, because acetone might not be so toxic, but it is able to carry other substances under your skin. And so again, you all are chemists, we all do chemistry, and we try to have less hazardous compounds, but some of them are hazardous. And this is why we are getting trained as chemists. We need to be able to use hazardous compounds in a responsible way, right? And that starts even with simple things we use every day, like acetone for cleaning glassware, right? So they're using benzene here, clearly. That's something you would not really do any longer. And you can see something else. It was acceptable for them to have a very low yield here. Nevertheless, this went into a multi-ton process here. So clearly, if you would be a process chemist today, this would be the first step. You would like to significantly improve, right? Then they do an elimination, acid catalyzed, they use oxalic acid here and base. And again, look at this, disastrous yield, right? And then they do a addition of methyl lithium. So first of all, methyl lithium is pretty, is again high energy and difficult reagent. They add the methyl lithium to the carboxylic acid. I'm not sure if you know that reaction. You can add methyl lithium to a carboxylic acid to make methyl ketones. But do you know how to do this? I should have put this up as a question. You need to use 3 equivalents at least. So it's not in the scheme here, but that is highly accessed. So you need 3 equivalents of methyl lithium because the first equivalent you need for deprotonation, the carboxylic acid. The second equivalent, you need essentially that the methyl minus then attacks the carbonyl compound. And that's difficult because it's a carboxylate you're attacking. And that, of course, is difficult. I was not daring to use this here. I was hoping that they would let me use my iPad, and I was not allowed to do this, right? So let me try this again. So if you have a carboxylic acid, and you do methyl lithium, so that's the first step you do. You make the lithium carboxylate, and then more methyl lithium. Is going to add, and that is a difficult process. And then when you quench this, and that is also a very difficult process, if you quench this with water, or in modern terms, you would quench this with TMS chloride, you might want to look up at this reaction, then you could form, you would form the methyl ketone here. That's a tricky, very tricky reaction. It requires at least 3 equivalents of a relatively difficult reagent, right? One of the issues, how would you do it maybe today in the lab? You would activate your carboxylic acid to an amide. You see this was not available at this time. You would generate a such an amide, and now you can use methyl lithium or also a grignard, and you only need 1 equivalent, and you accomplish the same type of transformation. And so that is probably by far the better way to do this. And you can see here that probably oh, now I need to go back. So, but you can see that they nevertheless apparently were able to do this quite well by working this out, right? And then they essentially do the same type of chemistry again because they need to add the same group again here. And you can see that overall, the yields they have been able to accomplish here is relatively low, and you can imagine how much waste that has produced at this time, right? And so there are more steps or different types of synthesis from this. Need to make sure that I'm not going over the tea break. This is the reaction I would like to discuss with you guys in the tutorial. This is how BASF is making this, and you can see they start from the same starting material. They also add a grignard, but then the reaction sequence goes differently, and most importantly, they're using a couple of Wittig reactions. And some of you already said Wittig reaction is an atom. We talked about atom economy or reactions. Some of you mentioned also the Wittig reaction. We need to look at the Wittig reaction, and you can see that they're using this in quite some way. They're making the aldehyde, but then they also condense this Wittig reaction with this aldehyde to make actually the beta-carotene in the end. And that is something I would like to have a closer look at this. Let me just show you quickly. Let me see. That's Hoffmann-La Roche, because I don't want to run over the tea break. Look at this. This is how you make this ionanine, and that's the BASF process. And I think this is pretty spectacular how industry is able to do reactions in a really benign way. So they're starting with these isobutane compound here. This comes from the cracking of oil. And then they're using formaldehyde. That again comes from carbon monoxide and hydrogen, which allows you to make this. And then they do a so-called Prince reaction. They do isopropanol. And again, I could try to draw this here. So you see you have the formaldehyde, and then you need an acid to activate this, and then you add the alkene to the aldehyde here. This is a so-called Prince reaction, and you're getting out this isoprene. Fantastic reaction, 100% atom economy, right? So keep always this idea of atom economy in mind from two readily available bulk type chemistry, but which you both get from fossil fuels. You get this both from oil in the end. So then they have isopropanol, and then they do an oxidation. And in the lab, you would probably consider chromium oxide. You can do this at room temperature, fantastic, but it makes chromium waste. Now look how they do it here. They do it with oxygen. Oxygen is the most benign oxidant. I could ask you, what is the second benign oxidant? Anyone know what is, if you cannot do it with oxygen, then you would like to do it with, in the list, it's probably hydrogen peroxide, which is the next one, because hydrogen peroxide makes water as a byproduct. And then probably, which is done a lot in industry, the next one is probably chlorine. A lot of reactions are done with chlorine because then it makes chloride as a byproduct, right? And it's essentially sodium chloride very often, right? But look what they do here. So obviously they wanted to use oxygen. They do this on a heterogeneous silver catalyst at very high temperature. Look at this. Here are the 500 degrees, which we talked about earlier. But what they probably do is they have a reactor with a silver catalyst. This just needs to be heated to 500 degrees. And then they pump their isopropanol, they pump it over, and it is at 500 degrees in the contact. But it's not like you cannot think about this like having a flask which you would heat to 500 degrees for a couple of hours, right? That's not how it works. You have your reactor, and then you distill your materials through this reactor on the hot surface. You heat this surface gets heated to 500 degrees, but doesn't mean that your whole reaction gets heated to 500 degrees, right? So that is, even from an energy point, is very efficient. So they make this aldehyde of this, oxidation of the alcohol. And then another thing they do is they do an isomerization with palladium, right? Palladium can do hydrogenation if you have hydrogen present, but just palladium alone is able to isomerize double bonds. And you see that they go from a 1,1 di-substituted double bond, they go to a 1,1,2 tri-substituted double bond. The higher the double bond substitution, the more stable is the product. So this has a thermodynamic driving force to go from here to here, and the palladium, just by adding and shifting the hydrogen from here is just able to isomerize this, right? And then they have these two type of chemistry. Look at this; it's still 100% atom economy. Also, this reaction, the oxidation here is oxygen. The oxygen is gone in here, and then they add the alcohol to the aldehyde, and then the resulting hydroxide group gets eliminated. So they're getting this compound here, and this is set up for a Claisen rearrangement. This can do the Claisen rearrangement, then they're getting out this compound, and because they have this double bond here, this what comes out here, as I say, you have the scripts, you can go through this in more peace, and if you want to look at this again, this can do a cope rearrangement, and that this gives you the citral here. And that is made by these type of compounds and related compounds are made by BASF on large ton scale. Citral you could have used isolated also from natural resources, but you would need huge amounts of land. That's the next thing, right? Very often we say natural is better, but if we isolate it from a plant, if you want to isolate a compound in ton scale, we need a lot of land in order to build the plants, right? And that is again, you can ask how green this is if you need to use plants for chemistry where you might and land for chemistry where you might want to use the land maybe for food production. And it's again something we need to talk about. Okay, so with this, I think we all deserve a tea break, right? Is a tea break? Okay, very good. And then in the next one, in 15 minutes, then we really start talking a little bit more about catalysis. Okay, thank you. It's working or it's not working? It's not working. Okay, why could this be? Let me see. It's a new number now. So let me see. It works on my phone, so it should work. And yeah. So let's see how this all relates to chemistry. Can I lower it? But also the question, can I run the reaction still at high temperature to make it very, very fast? Is my catalyst accepting this? And that is one thing I tried in my PhD. I tried to do the palladium cross couplings not more than 40 degrees. Room temperature would have been even better, right? And no oxygen, occlusion of water. If I would have been more daring, I could have done many of these reactions at 100 degrees, 120 degrees, which are good, readily available. If you have a catalyst which can only catalyze a very specialized reaction with difficult to obtain starting materials, this might not be worthwhile so much, right? We talked a lot about waste already, so little waste we want to have. We would like to have ideally no additives. We would like to have benign solvents, right? Which solvents is it tolerating? And again, many catalysts tolerate water. You can even run many catalysis reactions in water. But also, the question how green is water as a solvent is questionable if it comes to getting rid of it, right? And then we of course wonder how pure is the product? Are there byproducts forming? How easy is it to isolate? So lots of things to consider here. Okay, general types of catalysts. What do you know? Just general, not too specific. Nickel zinc, this is already very specific. I would say nickel zinc I would put into metal catalysis, right? Okay, very good. Okay, there are some of you making the distinction homogeneous or heterogeneous catalysis. Very, very important distinction because at a heterogeneous catalyst, that is something industry likes specifically because it can be easily filtered. I showed you this reaction, this synthesis of the iodine from BASF. They were using 500 degrees on the silver oxide catalyst. That's heterogeneous, which you can heat indefinitely, and it's not going into solution, so there's no separation problem. All right, so homogeneous, heterogeneous, then indeed metal catalyst. So you say palladium, and so I will all put this into metal. You say photocatalyst, that can be metal or organocatalyst. Some of you also said organocatalyst, it's already gone here. Biocatalyst, very, very important. Very, very important. And again, there are companies who are really experts in using biocatalyst in the BASF, for example. Again, they have a huge unit for biocatalysis, and it comes to the point that you should consider a biocatalyst like an enzyme, like a normal reagent or catalyst, and so it comes to this. Okay, so you guys have very, very good idea. Ziegler-Natta catalyst, interesting. You guys bring up very important catalysts. I show you the Ziegler-Natta catalysis in a moment, because indeed this is one of the big processes which is being used in catalysis if we think about what type of catalyst and what catalytic processes industry is actually using. So you have a great idea on all of these things. And so if I just go very general, I would have ordered it and say there are metal catalysts, and this can be Lewis acids or can be redox active catalysts. And the nice thing this is you can tune such metal catalysts by ligands, and you need to consider that you might contaminate your product with the metal, right? That's the one thing to consider. Organocatalyst, a Nobel Prize was given to Benjamin List and David McMillan. I talk about this a little bit more. This can be bronzite acids and bases, and it can be carbene catalysts and quite a number of other things these days. It's metal free, so there's no metal contamination product. And again, you can tune them by putting on functional groups. Enzymes, you put up, and probably more modern or more recent, which became very much in the focus is like light photocatalyst, but also the light itself as a catalyst, and also electrons, right? The electron can be a catalyst in electrocatalysis. You can argue, is this really a catalyst or should I put it here? But these are, we have the term now electrocatalysis, photocatalysis, so that certainly plays a role. Name the 3 most abundant transition metals for me. If you now talk a little bit about metal catalysis. Okay. Iron, copper, zinc, cobalt, iron. Okay. Rhodium, palladium. I must disappoint you. Rhodium and palladium is very, very scarce. Rhodium belongs to the 3. I shouldn't take this away because I think the question is coming. Which one are the least abundant? Okay, titanium, very good one, very good choice. So you have all a good idea. Many of you were saying iron. Iron is indeed the most abundant one. The second most abundant one, nobody. Oh, no. I'm getting ahead of myself. Manganese, indeed. That is the second most abundant one. And then probably it's not nickel, cobalt, copper, and so on. It's probably all in the same region. We have enough of this. We have a lot of this on Earth, but probably it's titanium which comes next. And I think I have a picture of this. But so if we say iron or manganese, now here's my next question. We have a lot of this, but can you name a catalytic process? Can you name a reaction these metals can catalyze? Okay, the Haber process. That's very good. Question is the Haber-Bosch process catalytic in iron? You're absolutely right. This is being done. The Ziegler-Natta process, which is titanium and aluminum, or zirconium and aluminum. So that's pretty good. But I would give it to you that probably the one thing which is closest is if you want to use iron, right? If you want to use iron, then it's probably Haber-Bosch process is a good thing. Hydroformylation, we talked about this earlier, is rhodium or cobalt. That's not, I'm not really aware, although we will go through an advertisement, because my group, we have developed a formal hydroformylation with iron. We will talk about this. The Wacker process, interesting. Now you start, oh God, I need to go to the next question, because now you start putting up processes I don't know. So the Wacker process is palladium. Oswald process, I'm not sure actually. And Cativa process I thought is iridium or so. I'm not sure. So you guys see that you have a lot of ideas about catalyzed reaction, but if you think closely about iron, very little iron catalyzes. Iron is doing stoichiometric. We talked about nitrobenzene to aniline. That can be done by iron, but that is stoichiometric. 1 molecule of nitrobenzene needs 9 molecules of iron. And very often, you see, that's very often what we say. We say it's catalyzed by iron, and this catalyzed by iron, we might want to say it's being made possible by iron, but it's not really catalysis, right? And so if we think about Earth's abundant metals in the third row, there are still very little reactions which can be catalyzed, and most of the reactions are in the regime nickel, copper, cobalt. That is all there. But iron, manganese, the metals we really have a lot, there is, funny enough, not too much real catalysis around. That might be something for you when you start doing PhD, or you already do PhD, or later on working in industry. I think that is something which would be very important to develop. Can we do a Heck reaction, which we do with palladium? Can we find a way to do it with iron? That would make a very, very big impact, right? And so this is what we have said. So these three abundant, let me skip about this because I already said it's rhodium. And there you probably could say a lot of reactions which are catalyzed by this rhodium, iridium. Here is the thing. So iron, manganese, and titanium. These are the three metals we have really a lot, and we are using. Of course, you all know what we are using iron for. We are using iron to build skyscrapers, right? So it's used for buildings and so on. It's not that we don't know what to do with iron. Titanium. What are we using for titanium? Paint, for example. It's white paint. It's titanium dioxide, right? So again, we use this a lot, but we use it a lot less for chemistry. Manganese is probably one of the things which might become important as a substitute for the Haber-Bosch process to activate nitrogen. We know that enzymes can activate, manganese-based enzymes can activate nitrogen to make ammonia, right? But overall, we do not know so many catalyzed reactions. You know many stoichiometric ones. You know oxidations with potassium permanganate, for example. But that's all stoichiometric. That's not catalytic. And then the chemistry we really know very well in catalysis are the precious metals, like palladium. You see here, palladium, rhodium, ruthenium. But you see, taking into account, this is a logarithmic scale. So if I go here from iron, which is like 10 to the power of 4 ppm abundancy, then rhodium, we are suddenly 10 to the minus 5 or so. Iridium, which everybody likes now in photocatalysis, is the scarcest element we have on the planet. There are only 6,000 tons of iridium. That sounds still a lot, right? There are only 6,000 tons of iridium on the planet. And the fact is, it was very long, it was very inexpensive because nobody knew what to do with this and so on. It was much less expensive. Look at gold. Gold is about 1,000 times more abundant than iridium. But gold was for the longest time because we make jewelry out of this. It was much more expensive. But now people realize that iridium, because we are using it not only for photocatalysis, we are using it for the lamps, for LEDs, very little fortunately, but it is a very scarce compound. So iridium, rhodium, also osmium. One of the reasons, probably the Sharpless dihydroxylation, for which he got a Nobel Prize, never made its way into industry, was that you needed around 0.5 mole percent catalyst. So the osmium would make 200 turnovers, but you can see how scarce it is. And if you want to make a ton, even just a ton, we're not talking about millions of them, if you just want to make a ton by an osmium catalyzed process, and if it needs 0.5 mole percent of the catalyst, this means probably you need 500 grams of osmium, right? And so that was very prohibitive, and as great as that development is, as little it was used. Some of you said, when we talked about what type of reactions you can do, somebody said Wilkinson catalyst, right? That is a very important. This was a rhodium catalyst for hydrogenation. This indeed made it into industry because there you can make 1 million of turnover, and then using rhodium, and then especially if you're able to recycle this, was acceptable. And so that is an example which made it into industry, but also Wilkinson got the Nobel Prize for developing such compounds and showing that such complexes can be used as catalysts, right? And we have seen other Nobel Prizes. We have seen the Nobel Prizes for the palladium type cross-coupling, because that's also very broadly applied in industry. And you can see that palladium is, from all the precious metals, is probably much better than rhodium or iridium. But you can see palladium and platinum is relatively similar, and gold is actually more abundant than palladium. So it's often very interesting when we use palladium, and for many cross couplings we use like 10 mole percent of palladium. That is a lot, and that is a lot of a very precious, very precious Very, very precious metal. Just note here also, we hear so much about rare earth elements, right? We heard this to make batteries and lots of this. It's called rare earths, but they're not really that rare. So you can see here cerium is as abundant or very close to copper, nickel, cobalt, and so they are relatively abundant. The problem is in a battery you need them almost stoichiometric. So that again is always the question. Okay, so here we have some again. So the top three, I should probably put this up, is the third one is actually not titanium, the third one is actually chromium. And so again, not so much catalysis. We use chromium for oxidation, so Jones oxidation. It's all stoichiometric, right? So we have a certain disconnect about metals we have abundant, but then about metals we can use for catalysis. So the least abundant ones, like here, rhodium, ruthenium, iridium, I made this table just for photocatalysis because these are typically metals we use now also in photocatalysis. And so we have a certain disconnect about abundancy and efficiency as a catalyst. Okay, so some of you said the Ziegler-Natta polymerization, and that is indeed a great process, and I would like to emphasize what catalysts can do and how far we are away in many of these issues. So the Ziegler-Natta polymerization started in the 60s. It got the Nobel Prize in 1963, and it made so much money that in Germany, the Max Planck Institutes, especially the one in Mülheim, Kohleforschung, could be funded by this. So Ziegler did not use the money which was generated from the patents for these polymerizations. He did not use it for himself. He used it for science. He gave it back and made research foundations. Natta, Italian, he was more like having a great life, and actually that's what the Ziegler and Natta thought about this, because Ziegler said everything should go back to science, and Natta said some should come to me, right, for these things. So what they developed is they developed the polymerization of alkenes in a very spectacular way. So this is here the most easiest one probably to make polyethylene, and what they were using is they're using a combination of here titanium and aluminum and triethyl aluminum, and what it does is it made very, very high molecular weights once, but you will see that this can go up much higher. And the interesting thing was you didn't need pressure any longer. This would do it at ambient atmosphere and at relatively low temperature. And the mechanism for this is pretty well known, that the titanium, you form a titanium alkyl species, and then an alkene is coordinating to this, and then the alkyl group which you have on the titanium moves to the alkene, and then the alkene carbon moves to the titanium again. So you see, you're just extending this. You go, here you have a shorter one, here you have the longer one, now the next alkene can come, and this repeats over and over. And so this is how it started, but then it became, and then the second generation was not using titanium and aluminum. This was using zirconium. It was using the zirconium bis-cyclopentadienyl complexes, and again, from the mechanistic point of view, it's the same idea. You have an alkyl group already. This is the growing alkyl chain on your zirconium. You coordinate the alkene to this, and then the methyl group is migrating to the alkyl chain, and the carbon of that, the second carbon of the alkene, is coordinating back to the zirconium. And you see, you have this type, and then the next alkene can come. It coordinates, and then you go on this. And in order to make this, and to make this more efficient, in order to make this pre-catalyst, you use this zirconium 4 compound, so it's 2 cyclopentadienyl and 2 chlorines, and then you added something which is called methyl aluminium oxide, MiO. This is essentially methyl aluminium with a methyl group. This is exchanging the chlorides for the methyl group. This is your starting catalyst, and then the reaction goes. And look at this. 1 gram of catalyst makes you 40,000 kilograms of polymer. That is so spectacular if you look at this, right? This is essentially, we're not taking exactly in the turnover numbers in case, but this is the type of turnovers this is making. This is, so 40,000 kilograms is 40 million grams, right? So that is 1 gram to make 40 million turnovers essentially. That is amazing. And look at the amount which is being done. This is done on a 100 million tons scale. That was the number from 2010. And the very interesting thing is it could not only make ethylene to polyethylene, but if you use propylene, then there is I have this on the next one. If you use propylene, then there is a question of stereochemistry coming up, because if you have the propylene molecule, the methyl group, so you polymerize the ethylene unit, but the methyl group here can be in front or in the back if you have the growing chain. And this can be randomly, that is what we call atactic. But that can be all on the same side. That can be isotactic, or it can be alternating. It can be syndiotactic. And the second generation catalysts which you have now, they developed catalysts which are able to make isotactic or syndiotactic compounds, polymers, selectively. And I've shown you just some of the catalysts here. So a lot of that depends on steric. You see they made sterically bulky, not only cyclopentadiene any longer, but they use the individual ligands, and then the chains try to avoid these large groups, and so therefore you build up stereochemistry in the growing chain. And this makes polypropylene almost in a crystalline form and very durable. It gives you very different properties than just if you polymerize in a random way, like with a radical polymerization propylene. And so this way you could make very durable polymers. And so, for example, in your cars, all the light, the insides in the car, this is all polypropylene, but it's all polypropylene coming out of the Ziegler-Natta type processes, and that makes it so hard and so durable. Or if you have these suitcase, if you go traveling, if you have a hard suitcase, nowadays we have a lot of these soft suitcases, this is polycarbonate, but the hard ones, which you can essentially not bend, this is all polypropylene. Okay, so then let's talk about homogeneous catalysts some more. And again, the question is it acceptable now to use precious metal? And here are some hydrogenation catalysts, and we already said that hydrogenation is probably one of the mostly used catalytic reaction, but it's also being used in an asymmetric way, and there, of course, it becomes very relevant for drug chemistry. And so here, typically, the metals which are being used are ruthenium, iridium, precious metals, which are very, very effective, and you can see here some chiral catalysts, which not only give good EE, but they give spectacular turnovers, 2.4 million here, one development of Noyori. This is the famous transfer catalyst which he used, which has two different ligands. It has a BINAP ligand, a phosphor ligand, and then it has a diamine ligand. And you see here the turnover frequency, not only that it can do a lot of cycles, but the turnover frequency is with 63 per second. So that means it makes about 20,000 cycles. I hope I calculated this correctly. No, it makes 200,000 cycles an hour, right? So 63 times 3,600. So very, very, very efficient. And then the ruthenium catalyst, iridium catalyst, which were later on developed, would push this up even further. So now we're talking million tons. You see they have more specialized chiral ligands, so the enantioselectivity also went up quite a bit, and so the hydrogenations clearly are very, very efficient, and there you can argue that it is absolutely acceptable to use such a precious metal because it is so effective in its turnover. And I show you, I think it's on the next slide as well, but also in the tutorial today, I would like to discuss with you the synthesis of nicotine. And nicotine is being used as an alkaloid for many applications, and it's being typically produced also on the ton scale. And one of the key steps in order to do this is to do an asymmetric reduction. You see you have a chiral center here. Do an asymmetric reduction of the ketone to the chiral alcohol here. And that can be done by such an iridium catalyst. And I think I have it on the next slide. So you see this is what they do. They use these iridium catalysts. They use this starting material, and once you reduce the carbonyl group to the alcohol, and then if you can deprotect this Bock group and then do a nucleophilic substitution, you can synthesize nicotine in a very fast way. And what they have been able to do with these type of iridium catalysts, which I just shown you on the previous slide, is they can do this with a substrate to catalyst ratio of about 100,000. And so this was done in batch processes. This company produced 40 tons of nicotines, but they always did 500 kilograms at a time. And here you can see what they've been using. They're using 45 milligrams of catalyst to make 1 kilogram of product. That's, again, very good. The one thing I would like to discuss with you in the tutorial this afternoon is this efficient enough that we do not need to worry about leaving the catalyst as a contamination in the product? Is 45 milligrams per kilogram sounds very, very little, right? But we need to take into consideration that if you have a drug, you can only have less than 10 ppm as a metal contamination in your drug. And so that's what we do later on in the tutorial. We should think about the question, is this sufficient or not, right? Heterogeneous catalysts, you put this up and said there are homogeneous catalysts and heterogeneous catalysts. And what are advantages of heterogeneous catalysts? Yeah, recycling, much easier, right? Typically, you just need to filter it. You guys like the recycling very much. Simple separation, yeah. Reuse, okay, so we are all on this. Very often they are also very robust and also active at very high temperatures. We looked at this iodine reaction, 500 degrees silver oxide, right? That is something you cannot do with a homogeneous catalyst. Right? So the thermal stability, very, very, very good. And again, the Haber-Bosch process, one of you likes this here, the Haber-Bosch process runs at 350 degrees. And indeed, that's with a heterogeneous iron oxide system. And so again, this is the robustness is a very good point. Reduced contamination, absolutely, right? And so indeed, if you think about homogeneous catalysts, that is very often they have very good reactivity, but also that's the one thing nobody said is homogeneous catalysts I can tune with ligands. So I can do asymmetric reaction, I can control stereoselectivity. I have much harder time to do this with a heterogeneous catalyst, like with silver oxide or so, right? And so typically we can do stereoselective reactions with them. But then if it comes to recovery, then it becomes already a lot more difficult. I don't know if you run reactions sometimes in the lab. If you do a reaction on a catalyzed reaction, then you do chromatographic workup. Your catalyst might be somewhere in the silica, but you never recycle it, right? So if you do this on larger scale, sometimes you can try to precipitate a catalyst. you can try to recover it by electrochemistry. That is something only specified companies can do. But I can tell you that in Germany we have the company Degussa. And Degussa makes precious metals, rhodium, palladium, and all these things. And not any longer, but 20 years ago or so, they were very, very, very generous to us in universities. We could write to them and we would say, we want 50 grams palladium acetate. And they send it to us. We want 10 grams of rhodium trichloride. They would send it to us for free. They wouldn't charge us. They had one request. They said, when you do the reactions and you do the chromatographic workup, we would like that you take, because the catalyst is on the top of your column, right? Take the silica on this, put it in some kind of a box or bottle or so, and send it, once you have filled this bottle, send it back to us. Because then what the Degussa did is they would put electrochemistry onto this, and the precious metals would get deposited on the electrodes. So they could essentially recover everything. And so their biggest concern was that we would throw it away because we would think it's a silica waste. But they could essentially to 100% recover this. And so that was a pretty good deal for us. So electrochemical deposition is very good, but not everybody can do this. Sometimes you can extract the catalyst. And sometimes also a very interesting concept is you can run a reaction in a biphasic system. And so then if your catalyst is in the one phase, you can leave it in that phase. You have your product in the other phase, and then you can extract it. I show you a few examples to this, right? And then we come from homogeneous to the heterogeneous catalyst, and there we have typically, I need to hurry up a little bit here. And there we have typically very often nanoparticles which are supported on some kind of a matrix. The one thing you probably know best is palladium on charcoal. This is nothing than palladium nanoparticles which are dispersed on your charcoal. So that's a typical heterogeneous catalyst, and we have this in many variants. The rainy nickel, this is nickel on aluminum oxide, ruthenium on aluminum oxide. So a lot of ways to have elemental metal finely dispersed on some kind of a heterogeneous matrix. Here's, for example, an example of something we developed in photocatalysis, where we had a polymer. It was just an alkane. We would have the alkane attached to an iridium catalyst, and so this catalyst was soluble in hexane. But then we ran a reaction where our product was soluble in acetonitrile. And hexane and acetonitrile at room temperature do not mix. They form two layers. You have a hexane layer and you have the acetonitrile layer. But if you heat it to 80 degrees, then they mix. So then you have one phase. And so what we did is we had our iridium catalyst. This had the alkane chain, so that was soluble in hexane, and then we had the reaction, a polar reaction, where our product was in acetonitrile soluble. So we heated this to 90 degrees, we had one phase, we shine light on, we did the reaction, and then we cooled it off, the phases would separate, the catalyst would be in our alkane phase, the product would be in the acetonitrile case, and so we just would have to do this phase separation, and then we could use the alkane phase again for the next photocatalyst reaction. So that is one way when you can use different polarities, different phases, you can do very efficient catalyst recycling. And I have to skip a little bit over this. One other thing which people like to do as a matrix, you have palladium on charcoal. That is very good, but that's really heterogeneous. One thing which also becomes increasingly important are nanoparticles. And so with nanoparticles, you can, they are smaller than what you have on the charcoal. And so they are almost soluble, but they're still heterogeneous in a way. So you have soluble heterogeneous catalysts. You can filter them and you can use them. And in our group, we used a lot of these magnetic nanoparticles, and we were able to attach reagents onto the magnetic particles like a tempo molecule, and then we were able to I just showed this here. Actually, you can buy it from Aldrich. you have an oxidation catalyst like tempo you use for oxidations, but it was attached to a magnetic nanoparticle. So after the reaction, you could just put a magnet to your flask, and then all the magnetic nanoparticles would go to the magnet, and this way you would be able to separate the catalyst off. So I go over this just a little bit quick. So we did this quite a lot. And so we were very happy with this type of immobilization of a catalyst onto a support, right? And so use especially also for chiral ligands, we would then try, because if you can have a homogeneous catalyst, but then you can heterogenize it by putting the homogeneous chiral catalyst to a support, attach it covalently. That's what we did, for example, with the nanoparticles. We were quite happy with this. And then there came out this publication in 2016. And you can see this came in Advanced Synthesis Catalysis. It was labeled very important publication, and it came from Johnson Pharmaceutics, a company in Belgium. And they published a paper, and you can see what it says. Why does industry not use immobilized transition metal complexes as a catalyst? Right? So everything we did the last 5 years or so before this, putting catalysts on nanoparticles and so on. And so here they tell us industry doesn't like it. And there might be a very good reason for this. And I could ask you this. Why that is? What do you think? Why they write that industry would not like to use a technology where you take a homogeneous catalyst, which might be very selective for an asymmetric reaction, and put it onto a support, and then make out of the homogeneous catalyst, make the heterogeneous catalyst out of this. And the metal toxicity. But in fact, usually you can separate it much easier. So the metal toxicity is actually a plus, because you are not contaminating your product so easily, because you filter it off in the end, because you have made your homogeneous catalyst heterogeneous. So I would argue that this is one of the advantages, that you avoid metal contamination, because you should be able to get it off. Cost of catalyst. This, I think, is a very good issue. Okay, so let me see about this. I think the one thing which I would think most is indeed the efficiency. So here, this is what came out of that paper. It needs extra steps to immobilize your catalyst, right? So you need to put it on, you need to functionize it so that you can put it on. And so if you have to do the extra steps, your catalyst must be better, really good in your turnover numbers. Otherwise, these extra steps are simply not justified. Very often through the heterogeneations, in fact, your turnover numbers and frequencies go down. So you're actually making the less efficient catalyst. And very often it's also not as selective as the homogeneous counterpart. And very often they're also not stable, because once you have your homogeneous catalyst and you do a run and then you try to recycle it, it might not be your metal ligand assembly any longer. It might be already nanoparticles. And see here, this is one thing where we experience this ourselves. So we put on such a pincer complex, which is really stable, a palladium complex, on an iron nanoparticle. And then we ran Suzuki reactions, and we ran them at pretty high temperature. We ran them in the microwave at 200 watts, so we had probably 150 degrees here. And then after one cycle, we looked at the catalyst, and you could see it was all nanoparticles. So we had essentially destroyed the metal catalyst and have made metal nanoparticles. And so we could have used palladium on charcoal right away, right? So there's really no big advantage of doing this. And so this is, and see, this is then the variant we came up. We simply immobilized palladium directly on the nanoparticles. So we made essentially palladium and charcoal just in a magnetic version. And this was very effective for this. So this is something you need to to take into account, and I have some more examples in the handouts where you can compare like a homogeneous catalyst, and then you compare to the various immobilized versions. You see here this ligand got immobilized on silica, and then it got immobilized on polystyrene, and then you can see what typically happens is reaction times go up. I talked with someone in the break about time efficiency, right? And so with a homogeneous catalyst needs 1 hour, and then the heterogeneous catalyst needs 30 hours. That is, again, that's not really acceptable. You see, EE is more or less the same, and then the big advantage is that the separation through filtration. That's, of course, a big advantage. But you can see you need extra step. You see, you needed to put on a silicon linker on the catalyst in order to bring it onto your matrix. And here they had an amine type matrix to bring it on the polystyrene. So you needed extra steps, and then you made the reaction slower. And that is that was one disadvantage. And so last idea here, metal-free organocatalysis. And you all know Nobel Prize Benjamin List, David McMillan, and they got it for organocatalyst. This is the famous McMillan catalyst here, and you will have one lecture on concepts in organocatalysis as well, and I'm sure that this will be covered, right? So this is a catalyst which can form an imine with carbonyl compounds, and then it becomes a very electrophilic way, and then it can add to the nucleophile like this indene on this center can attack here, this one. So essentially what you're doing, you need to be careful with this pen, is you see what your catalyst is doing. It forms such an iminium cation, right? And the iminium cation, you see it, the nitrogen has a plus charge. So this is now a better electrophile than your aldehyde was. And then this aldehyde was adding, so this center gets connected with this center. And this was adding this. And because the catalyst is chiral, it was enantioselective, right? It makes a difference if the addition of this acroline comes from the top or it comes from the bottom. This makes the two enantiomers. And then the reaction is finishing. You see here, once you do the addition of the indole, you see you have I would have so much hope they would let me use my iPad for this. You see, once you have the nucleophile, the indole as a nucleophile attacks, you have a positive charge here, and then if you have the nucleophile over here, then you can bring back the cyclization. And so this is how they made, how the McMillan group made this the cyclization product, right? Beautiful chemistry, fantastic, and was not easily been possible otherwise. And you can see fantastic enantioselectivity, very, very good yield, but look at the turnover rates and turnover frequency. On average, let's take the best case here. Let's take this case here because it's easy to calculate. 24 hours. 24 hours, and it needs 20 mole% of the catalyst. So that means the catalyst is making 5 turnovers in 24 hours. So it makes what? It makes 1 turnover every 5 hours. This is ridiculous, right? That is a very, very lazy catalyst, and this way, such chemistry will, in my opinion, probably never be practical, because think about the amount of catalyst you need, and think about how long it takes. And I think this is an important issue, which also the McMillan group has addressed very efficiently, and also Ben List these days is addressing very efficiently, to have these great principles, how these catalysts work, but make them more reactive in order to allow a faster faster reaction. There's another example from the Macmillan group, his famous Diels-Alder reactions. Again, fantastic selectivities, fantastic yields, but again, here it's a little better. It's 5 more % of the catalyst. That's 20 turnovers, but you see if you do 20 turnovers in about 20 hours, that's 1 turnover per hour. That is very, very, very slow. And the work of Ben List in these days is in order how he makes this faster is that he generates these super Lewis acidic and super Bronsted acid catalysts, right? So if you have pKa values here from weak acids to strong acids, he's now developing these very big catalysts which are very, very strong Bronsted acids, which essentially protonate everything in a very short time. And you see here is, for example, here's an example where he's been able to do a Diels-Alder reaction, and this Diels-Alder reaction would not be possible unless you protonate the carbonyl group in order to lower the LUMO. But usually if you would use a normal acid, if it's not a very strong acid, then the protonation would not be very efficient. But the developments of Ben List have these super strong Bronsted acids, which actually very easily transfer the proton to a carbonyl group. They highly activate these compounds, and then the Diels-Alder reactions become very efficient. Here's still an example which might not be so great, but you see low temperature, but still relatively long reaction times. But he has now, I'm not sure if I have this, he has now, here's a reaction. Somebody earlier mentioned the Aldo reaction. Here's the Mukayama-Aldo reaction, which he can catalyze now. And again, it's the same idea. You have this super acidic Lewis acid that protonates the carbonyl group, makes this center more electrophilic. And then you can see here, he's catalyzing now with 50 to 500 ppm. So 1 ppm is 1 in a million. So the 50th part of a million is catalyzing this reaction. You can see the reaction times is still very long, but if you calculate the turnover numbers, this is pretty spectacular, and also the turnover frequency, considering that you're essentially using very, very low catalyst amounts. Nothing can really compare to enzymes so far, right? If you think about biocatalysts, as also people mentioned, so there are, of course, enzymes, for example, the catalase, which we have in the liver, which is transforming hydrogen peroxide to hydrogen and to water, and essentially is oxidizing everything which should not be in our body. Look at these turnover rates, 40 million turnovers per second. That might tell you what you maybe in your lifetime will accomplish for small molecule catalysts, right? This tells us where it could go, to. The big advantages of these enzymes, biocatalysts, is they have incredible turnover numbers and frequencies. They are very selective. But the problem is that they are also very substrate specific, because evolution, biology over millions of years made this for a certain purpose, right? Get rid of toxic compounds in our liver and therefore decompose hydrogen peroxide, but not to do lots of oxidations of all kinds of alcohols, right? So that's the problem, is the big specificity. Okay, so with this, I think this was again a more general introduction for catalysis. So I think we have earned a lunch, right? So lunch, very good. And then I hope you still like to come back, and then we talk a little bit more about renewable resources. Can I start? Okay, so hello everyone. Welcome back. I hope you had a good lunch. I guess everybody is ready for a nap right now. This is so I try to entertain you a little bit with a lecture a little bit on renewable resources. So But let me see if everybody is still with me. So I have again a general question for you, and that is what you would like to see accomplished in your lifetime. Your lifetime is still very long, you're very young. You see it has now a new number again. So just as a starter, if everybody is still with me and online. Okay, nobody wants to see accomplish anything in your lifetime. Is it working? Let me see this. Should work. Yeah, better future. Get a well-paid job and get enough time to sleep. Yes. Let me at least tell you on the sleep issue, it doesn't get better. It gets worse. Success, okay, of course. So clearly you have personal goals, and that is absolutely okay. I had also, when I was your age, I was hoping to finish my PhD. I was hoping for a better job, and I think this is all very good. And then, of course, if you think about bigger things, do something better for the society, and maybe see. And that sounds always almost very flat, right? To see that the world somehow becomes a better place. I think that is something which, at least in my lifetime, went up and down. There were times when I thought that the world is becoming a better place. That was around 1989, when Germany was divided, the Berlin Wall, the wall came down. Somehow we had the feeling that with Glasnost, with Russia, we are getting good relations, and so at that time I was very optimistic about the future. Now you see this 30 years later, we are running again with big crises, with conflicts, and so that is something which is changing, unfortunately, and there's no constant path up. But I think chemistry is doing a very, very important role to actually contribute to these type of goals, and I would like to show you and give you some ideas about this. Get a PhD position in Germany. If you want to talk with me about this, I'd be happy to do this. And there are some things you can do, and some things it's still money, and especially currently with all these crises we have, money funding is very tight. But if you are really interested in doing a PhD in Germany, I can at least tell you a few things how to make your chances to get accepted for a PhD in Germany, how to make that, how to improve your chances. And in the moment, from one point of view, your chances are not so bad, because we are running in Germany through a decline in population and a decline in young people. And many of the younger people do not want to do chemistry. They want to go into computer sciences, informatics, all these things. So in general, very different than maybe 10 years ago, where we had very many PhD candidates from Germany for chemistry. This is not really so much true any longer. And so I believe that chances are very good for, or are good for this, and we might either discuss it, or actually we will have to see how the course schedule is. I actually have a small presentation for this as well. And so I think that's good. Some of you want to do teaching. I think that's also a good thing. I like to do teaching and enjoy this. Becoming richer than Elon Musk. I'm not so sure. And let me tell you, rich is very relative terms, right? For me, rich is to have a good life, to be able to live, have good accommodations, be able to eat, have food, and so on. I don't need to drive a big sports car or anything like this. So I think this is a very good thing. Learn more in less time. Yes, that's all what we dream of. But anyhow, somebody wrote that you want to continue learning. And I think, again, the university environment is something very good because I'm still learning. And so that is something very good. Want to complete PhD in foreign and return to India. I think that's also a very good aspect because during going abroad, and I did my postdoc in the US, but I also wanted to return to Germany and there give something back and go into these and do something there. And so I think that's also a fine strategy. Might also not happen. You might stay abroad, but also getting a good education, getting good training, and going abroad always makes your experience richer. I think you have very good education in India as well. Your universities, the IITs here are very good, but getting a different perspective is always very good. Okay, so after small leg you didn't want to see, you have a lot of ideas, both personal ones and maybe also more general ones. So let's talk a little bit about renewable resources, because we hear this a lot now. We should go away from fossil fuels, we should go and we should use renewables. And sometimes when you hear our politicians, at least in Germany, you get the feeling that all you need to do is flip a switch. And then you go from oil, you go to renewables, right? It's not that easy. And I would like to use this lecture to discuss a little bit with you what we can do already and what we cannot do, and where the challenges are these days in order to use renewable resources for chemistry. And in order to start this, I would like to ask you something else, because you all told me just about your personal dreams, but if you think about, and I hope you feel good about this, if you think about what can chemistry contribute to society, and I've given you a few things here which I thought might be something useful to put up here, and so that is exactly the question for us in chemistry now. I think there are a lot of contributions we make, but many of the contributions we indeed make starting from fossil fuels, because this is how the chemistry industry more or less works. So you guys like especially battle diseases, and I think that's very true, and I give you, I think, a pretty impressive example in just a moment. Clean energy, big issue, right? I think if we somehow will be able to have clean energy and in abundance, then we will probably solve most of our problems. Provide clean water. I think, I'm not sure, I will not see it in my lifetime, but you probably will see it in your lifetime, that this becomes one of the most scarcest and problematic resources more and more in the future. And I think that's very, very important. World hunger, absolutely. Chemistry, the contribution of chemistry to feed the population, starting with the Haber-Bosch process, which so many of you have mentioned earlier. This is a major contribution, and it's a contribution of chemistry. That's always very clear to see about this. And ultimately, world peace. I think so, because most of the conflicts we see go over resources. And if we, as chemists, make a contribution how to use resources efficiently, how to find new ways to use existing resources, I think this is a major contribution to world peace. So when I was like your age, I thought maybe becoming a pop star and singing. I'm not good in singing. Some of you wrote that you like singing in your free time, and then maybe you become rich and famous. But I think you have chosen chemistry as your profession, and I think you might be able in all these areas, and there are certainly more, make very substantial contributions, and you should really feel good about this, and that you are in that profession. So let me tell you again. So you said clean energy, right? So one of the things when we talk about biofuels these days is that we use as biofuels, the most abundant biofuel we use is ethanol. And ethanol is something we make from sugars, and that is very much a renewable resource, obviously. And then you can not only drive your car with this, you can also eliminate water from the ethanol and make ethylene out of this. And ethylene is the starting point for many of the polymers. We talked about polyethylene earlier. And this is essentially in the same way you can start the same type of chemistry from oil, right? You can get from oil, you can get ethylene, you can do an acid catalyzed water addition to get ethanol. So this is an area where the two areas come together. And this looks great, right? Ethanol, we call it bioethanol. In Germany, we call it bioethanol. We have 10% of ethanol in our gasoline nowadays. You have ethanol in your gasoline? How much percentage do you know? How much? Also 10, yeah. So that is of course one way. There are countries in the world which can have cars which drive to 100% on ethanol. Brazil is the one country. Brazil doesn't have any oil. Brazil has not enough money to import it. So what they do is they have a huge industry which is both making ethanol and ethylene from sugar canes. And so that sounds very renewable, very green, but we all hear in the news what the problem is, right? They have to clear large areas of land. The rainforest is being cut down in huge dimensions, so that they can make the land in order to grow sugar canes to make ethanol ultimately. And so that is also, I think, a very complicated issue, political issue, because I feel, at least from the governments, and we do this a lot in Europe, we point our finger to Brazil and say, you should not destroy the rainforest because we need it for our well-being and so on. But on the other hand, Brazil will say, hey, we also want to become more economically viable, so why do you tell us what we have to do in our country? It's our rainforest, right? So again, I think on a political debate, if we from Europe and Western worlds want to save the rainforest, we need to contribute and probably give Brazil money so that they are not doing this any longer, right? So it's not a very easy thing to do. Health. Everybody of us lives on average 10 years longer because we have antibiotics. And antibiotics, really, penicillin came in the 1920s. And Alexander Fleming, he was a chemist who has isolated penicillin from a mushroom. And then there's two other people, Chain and Florey, they were medical doctors, and they treated the first patient. And this treatment was very, very successful. But at that point, they had so little penicillin. You have to think about this. They isolated this from the mushroom, and then they treated the patient, and the patient got better overnight. It was fantastic. And then they ran out of the penicillin, and they tried to re-isolate it from the urine of the patient. And so they could maintain it a few days longer, but they couldn't make enough, and the patient died. So the first patient they treated with penicillin, they saw the positive effect, but there was not enough around. And nowadays, of course, we can synthesize, either by biotechnology or by chemical synthesis, of course, penicillin and enough antibiotics in order to treat the world. And not only with penicillin, we have enough of other antibiotics itself. And it's estimated that the life expectancy of everyone in the world was raised by 10 years because we have antibiotics. Haber-Bosch process, this was the one, you guys liked very much as well, right? So the Haber-Bosch process makes ammonia from nitrogen and hydrogen. And you see here, again, high temperature, which we have seen so many often times so far, but high temperature is something, it's energy intensive, of course, but it's something industry handles quite well. But also high pressure here, 300 bar, and it makes ammonia. The Haber-Bosch process takes 2% of the world energy consumption. Think about this, 2% goes into this process. But without the Haber-Bosch process, we could only feed half of the population we have on Earth today. So it's a pretty good investment. And half of the proteins, 50% of the proteins you have in your body are not natural any longer. The ammonia comes from the Haber-Bosch process. It does not come somehow from natural biosynthesis or so, but the Haber-Bosch process is really contributing to this. If you would be able to find catalysts which would lower that temperature, and even just by a little, that would make such a huge contribution to the energy bill which we have in the world. So that's really something, and people try this very hard, and I think that we will see very soon electrochemical methods to do this type of process, essentially at room temperature, and that will make a major change in the energy consumption. And as I say, I think ultimately everything is about resources. And so if we look, no matter what crisis we have, in the moment we have that Ukraine crisis, I think it becomes more and more clear that all the countries are interested in the rare earth metals, which are which you can find very many in the Ukraine. I think ultimately, if you look also in the history, if you look about wars and conflicts which have started, I think it's almost ultimately it's resources. And so that is, of course, something chemistry is very, very important, can play a very important role. So, having said this, name important renewable resources. Let's see what you come up with. Sun, solar energy. Yes, it's probably not renewable, but we will not experience in our life that it will not be enough there, right? I think the estimates are it still can go on for millions of years. Wind, something very big in Germany. I'm not sure, I haven't seen so many windmills in India so far. And geothermal energy, okay, you guys like all the energy aspect. Wind energy, geothermal, biomass, okay. So but let's say that's wind, sunlight, and the heat which comes from the ground. Okay. What about molecules? Okay, tidal waves, yeah, that's also, this is all energy. What about chemicals? Nuclear energy, yeah, it's also the question if it is renewable, but indeed there is still a lot nuclear fuel available, and it's not really easily seen that it can be used for anything else. Okay, so you guys are all, I can see this, you guys are all energy here. Okay? Let me talk about a few renewable resources more from a chemical point of view. So the one thing which we hear a lot about is carbon dioxide, right? And so carbon dioxide, we have a huge amount in Earth's atmosphere, 10 to the 12. So that's 1 trillion, so it's 2.7 trillion tons carbon dioxide in Earth's atmosphere. That's a huge amount, and that is something we can consider these days also as a feedstock for chemistry, right? Can we do chemistry with carbon dioxide? The problem with the Earth's atmosphere is it's very, very dilute, so it's not so easy to get out. But we can think about if we produce it in heat processes like in an industrial process rather than releasing this in the atmosphere, should we capture it, at that moment and do chemistry out of this. The problem with this is, and I will show you some examples what people can do with carbon dioxide so far, is carbon dioxide is a very, very stable compound, right? Everything we burn ultimately goes to carbon dioxide. So in order to bring it back to something again, to recycle it for chemicals, is typically very energy and extensive. Oxygen is clearly a renewable resource, comes from the biosynthesis, photosynthesis. We talked about this, carbon dioxide and you're going to sugars and then making oxygen, so that's renewable. Nitrogen, by the same thing, you can argue if it's renewable, but it's very, very much abundant. You see, of course, it's about 1,000 times more abundant than carbon dioxide. Water is even 1,000 times more available on the planet than oxygen and nitrogen in Earth's atmosphere. So we have a lot of this, but the problem already is that less than 3% are drinking water. And a lot of that is like in the oceans, and there you could in principle think about desalinating it, but it's again, it always comes back to the idea that if we have abundant energy, then we probably can do anything, but if you do not have it, then it's more a problem. The picture you see here on the right, let me see this. This is Regensburg, and this is the river Danube, and probably like every other year or so, we have some high water in Regensburg as well. And you see here, there are already some of the houses underwater, so that happens. I was here from indoor, we did this outing. Where did we go? Which river was this? It was the second biggest river in India, and there the high water was incredible. So we are not, it's not that bad. So we are not getting that much of high water, but we get also a fair amount of high water in Regensburg. So yeah, so again, as I say, it's less it's drinking water, and I think water is really one of the most precious renewable resources we have, and I'm not sure if we, especially you and also me, because I grew up and we always had water available, but this is not something which is so obvious. And so even like it only started to become widely available around 100 years ago when disinfection of water by chlorine took place, and so then this way you could essentially chlorinate the water, and then the drinking water from the taps you could actually drink, and there were many diseases in the 19th century like cholera, and that was eradicated by the water disinfection, and that was something where millions of people died in the previous century. And unfortunately, I think we see that in some countries as well. We have enough water on the planet, but it's very unevenly distributed. So there's no water shortage in Germany, but I think already India, where it's such a hot country, and that is already maybe more of a problem. Other countries like Mexico, and then there are certain rivers which go through the US first, and then they come to Mexico, and the US takes out all the water, like the Colorado River. So it's also an interesting question, right? Who does the water belong to? If you have a river which goes from one country to the other country, is the first country allowed to take out all the water and then no water comes to you? So that will be very difficult problems. And again, it's a big potential for conflicts. And so, I don't know, besides chlorine, I don't know if you know this, how else can you disinfect water? What is the normal way? And you guys can probably cheat, at least the ones who have a water bottle in front of you, because this is not disinfected by chlorine. Chlorine you can taste. The chlorine taste, if you ever go to the US is doing the whole disinfection by chlorine, the tap water they have. And if you drink the tap water, it's okay, but you taste the chlorine in there. But the chlorine and derivatives, so chloramine, I'm not sure chloramine, but chlorine dioxide, I'm aware that this is doing this. Irradiation, and then very often, indeed, irradiation in combination with ozone. That is a very good way because it gives you taste-free water. And so I think it's on some of the labels on the water, it says purified by ozone. And that's a good thing, and so on. And indeed, so filtration, boiling, and indeed, if you have no chemicals or so, that boiling is of course a good way. And even you can take water in big plastic bottles and then put it on the roofs. If you have a black roof, you put it there and you essentially disinfect by heating and UV in combination. So very good. So there are good methods now available. But again, for example, the ozone treatment, that is costly. That is not easy. And again, it's energy, because how do you make ozone? You make ozone by electrifying oxygen, right? So it's very clean. We have enough of it. We can produce it, but it's a high energy process. As so many of the process we have, reverse osmosis, very important indeed. That's also done a lot. So you guys are very good. You know all about this. Here's one thing I find fascinating. If you talk about conservation of water, that's of course another way. The one thing is we can say we produce enough, and the other way we can say we should doing more conservation, and I think that's very important as well. Here's an interesting ad, which again comes from BASF. BASF is not paying me that I mention them so often, but they are of course very much present in Germany. So that is something which came up also in the 2000s. It was before my time when I was a baby. These disposable weight diapers. And you can also see one of the problems industry or society we sometimes have when we advertise chemistry. You can see here they say chemical free. That's not true. These are these diapers which have these super absorbers in there. And these super absorbers are polyacrylates which essentially form a network like a football net. They form a network and they're very efficient to trap water. So these modern super absorbers, 1 gram of a super absorber can trap 2 liters of water. That's pretty impressive, right? It cannot trap as much urine because that has salt in there. So the moment you have salt in there, the efficiency goes down, but nevertheless. And the point is, babies like it so much that nowadays they become toilet trained a year later than my generation, because we hated it, of course, we didn't have this, but the babies now don't care any longer, right? Because they don't feel it. So that's nice for society. But I think what is much more exciting is that the super absorbers allow you to do agriculture in desert climates. And so what they do here is, you see here they grow this in the desert. What you do is you put the water in the super absorber and then you put a plant in there. And the plant with the roots will be able to pull out the water, but the sun will not be able to evaporate it so fast. And so now suddenly with very little water, and also it does not get evaporated so fast, you can actually now do agriculture in desert areas. And I think this is really, again, the diapers is nice, but I think the plants, this is really great that this is possible. Okay, so we talked about oxygen, and so it looks like there's a lot of oxygen in the atmosphere, right? So there was 10 to the power of 15. That is, let me see, 10 to the 9, 1 billion, 1 trillion, 1 quadrillion tons of oxygen. But we burn a lot of stuff, right? And so the oxygen goes away. And so the question is, how much oxygen would you be willing to give away that we can use for chemicals and burning and all these things? How much from the 21% we have in the atmosphere, how much would you be willing to give up to have a pretty good, still a good life? And so interestingly enough, the overwhelming majority says 19%. So if the oxygen concentration goes from 21 to 19%, that would still be acceptable. And you are absolutely right. So it cannot go lower than that. And let me give you the rundown. So 19.5%, that's what's considered to be acceptable 15%, you already have major problems coordination. Some people were willing to go to 8% or 6%. You can see then you die in a few minutes. And so definitely, and it's logical that it is this way, because evolution trained us, made us this way, right? There was always enough oxygen available. So the way we adapted, a human being or living beings adapted, where we were adapted to a 21% oxygen atmosphere. And so this is, the good thing is, even if we keep burning everything, we will not lower the oxygen concentration, because there's really so much that we cannot burn it. The bigger problem is really the air quality, that we have particles in the air. And I was last year in October, I was in Chandigarh in March, in November, and there they were burning all the stubble from the fields. And you could breathe, of course, but you had all these particles in the air, so the air quality was not optimal. The oxygen concentration is not a problem, but the air, the particles we have in the air, that becomes a problem. Okay, greenhouse effect. You probably know how that is. That's of course what we hear about a lot in the moment about global change and climate warming. And the way this works is we get the solar radiation, we get it on the Earth that can pass through any of the gases, and then it gets reflected to from the Earth again back to the atmosphere, but it gets reflected as heat. It's not as UV irradiation, it gets reflected as infrared irradiation, and there some of the molecules are able to trap that heat, right? This is how the greenhouse effect works. And so I could ask you, which compounds in the atmosphere contribute to global warming? So what are the compounds which do this? Okay. Good. You guys are good, are very good. You can answer more than once, I think. And of course, everybody knows about carbon dioxide. That's what we hear enough. Indeed, you're very right. Methane is a very major contributor. Of course, there's very little methane in the atmosphere, but that actually has a much higher global warming effect than carbon dioxide. NOx, certainly, also methyl bromide. Interesting enough, if you make plants like bio-wraps, where you make biodiesel from, they produce some methyl bromide as a natural methyl bromide as an insect repellent. But methyl bromide has a very high global warming effect. Hydrogen, and I'm not sure if I cannot see it, oxygen zero, nitrogen zero. So very good. So you know that this is not true. Hydrogen is the same thing, has no global warming effect. And let me see that, let me give you the explanation for this. You need, a molecule can only absorb infrared light, and you will have a lecture on spectroscopy, if it can change the dipole moment by vibrations. And so carbon dioxide can do this a lot, right? So if this is my 2/5 of the oxygen molecules and I'm the carbon here, then if it is doing this, it's changing the dipole moment, right? If it's doing this, it's changing the dipole moment. So we have a number of vibrations. If it's doing this, it's not doing this. So the symmetric one is not absorbing this, but everything else is. And so a 2-atom molecule from the same atoms, like oxygen, nitrogen, hydrogen, whatever it does, it changes, it cannot change with no vibration, it can change the dipole moment. So these are all IR silent, they do not contribute, but carbon dioxide, methane, methyl bromide, NOx, they all can do this. So here's a question. How much warmer on Earth is it because we have carbon dioxide present in the atmosphere? See, we hear so much about the global warming and all this of carbon dioxide, but I can see there's a lot of different answers here. Okay. So the answer is 8 degrees. And I guess the people who have written 5 degrees, they think already this is what it's doing right now. And then 1.5 degrees, this is what we hear a lot in the news. So the 1.5 degrees, this is what it is estimated the additional extrusion of carbon dioxide by mankind or humankind is causing. Addition to the normal global greenhouse effect. But the overall greenhouse effect contributes for 33 degrees. Without the global warming, without the greenhouse effect, it would be 33 degrees cooler on Earth than right now. So even life in India would be probably not possible. Life in Germany would definitely not be possible at all. And so the greenhouse effect and carbon dioxide contributes 8 degrees to this. I will not tell you which is the most one because I think it's my next question. But this is the contribution of carbon dioxide. Without carbon dioxide, it would be 8 degrees colder. The 1.5, and sometimes now even the 5, we hear that say more carbon dioxide emitted by humans. In 30 years, we will have 5 degrees more warmer. This is all the estimate which is estimated comes from humans. But the natural global warming effect of carbon dioxide is about 8 degrees already. And now the big question is what is debated is how much warmer will it become if we emit more? And that is something which is not so easy to assess because in the moment we have more or less filled the absorption of the IR bands already. So the question is, will more carbon dioxide how much more will it warm up this? Because the bands are already saturated. So one could argue it will have no effect. But on the other hand, what is also known is that if you bring more carbon dioxide, you will make, I need to use a laser pointer, these bands become broader. And so there is additional absorption. And it's very heavily debated how much this will be. Okay, so 8 degrees. Oh, okay, so I don't have that question. So the number one global warming gas we have in the atmosphere is water. So water, without water in the atmosphere, it would be 23 degrees colder on Earth. So the water has a major effect on the greenhouse, and in fact we definitely need in order to have a planet on which we can live. So now when we talk about renewable resources, there's a petrochemical cycle and there's a bio-based carbon cycle. And if we look at the let's first look at the bio cycle. So typically what we would say is we have carbon dioxide and sunlight, photosynthesis. This makes plants biomass, and that is something we can refine and make sugars out of this, and then hopefully with catalysts we can make fuels and chemicals. And I will show you that there's a lot of effort is going on, but that is still something which is in its infancy in development. And again, you might in your lifetime make a major contribution to this, because that is something we cannot do as well as we know how to make chemicals from oil by oil refinery and subsequent chemistry. You see, both of these cycles are very similar. The only difference is that in the petrochemical carbon cycle, we have the plant biomass, and by a geological process, this becomes to oil. And this is the one step which is missing if we go directly from plants to sugars. So it would be nice if we could do this because we know how to treat oil. The problem is that this geological process takes millions of years. And so that is the unfortunate thing. If we could speed up this process, we would not have to talk about renewable resources as an alternative. We could stick with the oil, but that is something we cannot really do. So we need to learn how to come from plant biomass, omitting the geological processes, We can go to sugars mainly, that's the main part of the biomass, and then go to chemical. And so here are a few renewable resources based on from the organic chemistry, which you could have mentioned when I asked you what are typical renewable resources. So a lot of this are sugars. This is by far the most one. And so you see, this is a compound, chitosan, that is produced and used 10 to the power of 11 tons a year. So that's 100 billion tons a year. It's huge, right? And it comes from shrimps and lobsters. But you all know, if you want to process this, you all know, if you have ever eaten a shrimp, that is not so easy, right? This is a very hard material. This basically does not dissolve in anything. And so to do chemistry out of chitosan, we can make materials for building things and so on. But to use it for chemicals, that is not so easy. So what people typically have to do is you isolate this amino group here. So you start from chitin. This comes from the shrimps. And the chitin has still the acylation groups here, and then you make chitosan by taking out this acylation group, and so this is the material which one can process a little bit better. About the same amount we use is starch, and that is essentially, that's the polymer of glucose, and it has this axial connection of the anomeric center to the C1 next glucose molecule. And again, we are producing on the billion ton scale this type of starch compounds. And you see most of this comes from corn, wheat, rice, potatoes. Sorry, there's a spelling mistake. And already now, we only use about 50% for food purposes, and we use 50% for non-food purposes. And you see, there is again, this is one of the problems. We talked earlier about this idea of if you want to protect the rainforest for keeping the rainforest active and not making land for the sugar canes, but equally we are usually using the land to produce food. And that is, if we now switch and making more and more ethanol for energy purposes, this has a direct impact on the food production. And so that is already done very, very much. Cellulose, we use a trillion tons already per year. And the cellulose is essentially the same thing like starch, only that it does not have the axial connection. It has the equatorial connection to the next glucose molecule, right? So it is here on the anomeric center, that's equatorial, and then the next one, it's also again equatorial here. And this makes a very big difference, because this hydroxyl group can make a hydrogen bond to this oxygen, and this now suddenly makes this such a hard material. And it's not like starch, which is a powder and so on, but this makes a very hard material. This is good because most of the cellulose we use as materials. We use for wood, we use for furniture, we use it to build houses. But to use it for chemistry as a starting material, that is a lot harder. Because especially, we all know we can eat starch because we have enzymes, we can degrade it. We cannot eat wood, right? The reason we cannot eat wood is because we don't have the enzymes to degrade it. And so all this bioethanol is produced by enzymatic degradation, and that is something which works. But the same enzymes do not work for the cellulose. And so that is something biocatalysis tries to engineer. Because we know, of course, there are animals, termites, right? Termites, they can chop up wood, and we need to learn how these enzymes in the termites work in order to do this as well. Not really a renewable resource, but I just put this up here. Sand is still look at this big difference. We have so much sand in the world, we will never be able to use it. And so that's, again, 10 orders of magnitude more on the planet, and you all know this. The bad thing is that not all the sand you can use. What do we mostly do with sand? We build houses. You have to have a certain modification of the sand so that you can make bricks out of this. And a lot of the sand, for example, which you have in the deserts or so, you cannot use for building houses. And so, although we have so much sand, in certain areas, they have to import the right sand so that they can build. And so that's not so easy. The other thing which is of course good is sand is silicon dioxide, right? And so we can make solar cells, and we can probably make so many solar cells to plaster our planet multiple times. So the silicon is really an abundant metal which we have on Earth. Okay, we talked about ethanol as a biofuel, and I just want to ask you one thing. The question is if we can make it enough, but what is the biggest problem of ethanol in using this as a biofuel? Okay, so nobody thinks it has an unpleasant smell, right? We drink it a lot, right? And more or less, I don't know. It's not allowed on campus here, as I learned, right? No alcohol on campus, but of course, yeah. So there's no unpleasant smell. It's also not as explosive as gasoline is. So yes, you can of course bring it to explosion, but gasoline is a lot more explosive. Low energy content compared to oil. That's certainly true. From 1 liter of oil or gasoline, you can drive a car about 4 times as long as from one liter of ethanol. One of the big problems is indeed the high miscibility with water. Because think about this, if you have a pipeline, so this is something we would like to do, right? To produce ethanol somewhere where you have a lot of land and your plants, and then we would like to produce the ethanol in a pipeline. Think about using ethanol in a pipeline or putting oil through a pipeline. If you put ethanol through a pipeline and you have somewhere a hole in your pipeline and it starts raining in there, the water is 100% miscible with ethanol, and then everything is ruined, because to separate ethanol from water, first of all, again, very energy intensive, but it's very difficult because it makes these azeotrophs. With oil, very simple, right? The oil comes, you have water contamination, you have 2 phases, right? Because they are not miscible. So getting rid of the water is not a problem. So that is indeed one thing which also makes the use of ethanol more technological demanding, especially when you want to transport it. Okay, let me ask you another thing. 2020 number 1 cause of unnatural death on Earth. Okay, you all were also already all old enough for Corona, right? You probably have all experienced this here in India as well. It was 2 very difficult years, I would say, and also 2 lost years, okay? The good thing is, overall, Corona killed a very small number of people. I mean, sure, we all were affected. The whole world was not doing anything. We all have seen these terrible pictures and people in hospitals and so on. But the overall number is very little. Cancer is probably also quite a lot more already. Malaria, that's more relevant for you guys in India, right? Malaria, many people get affected, and there are also quite still a very good number of deaths in there. So that's definitely also something. Wars, as we experience in the moment with all these conflicts, and there are estimates that in the Ukraine war, more than 1 million people died. That's of course very much. But it's still nothing compared to hunger. So even in 2020, we have a massive shortage of food. And this is not easy to say, because we cannot say in a country like Germany, where we can produce and we have enough rain and everything, and now we use everything and ship it to the world. So there are no easy solutions to this, and you need to distribute it, land use, and so on. But the one thing you still should be aware is that it is still today a major problem, and which needs to be addressed, right? And so I have a few numbers for you. Yeah, if you have 200 kilograms of grain, so corn or wheat or so, you can produce 50 liters of bioethanol. This allows you to drive your car about 200 kilometers. But you can feed a person for a year, right? And so if the US would think about change entirely the gasoline to bioethanol, there would not be enough corn or wheat or so in the world to satisfy that demand, right? And in Germany, we have 10%, so we have 10%, and the entire state of Bavaria, which this is the state where I came from, we had in the beginning of the other talk, we had the map, I show this to you again. This would have to be plastered with cornfields. We could not have any cities, any streets, any buildings, anything. So this simply shows you how much land you need, even to just probably change to renewables like bioethanol. It's very interesting. The World Food Program, they give out a so-called, what they call the hunger map, the World Hunger Map. They give it out every year. And this is an organization which got the Nobel Prize a few years ago for their efforts to reduce hunger. And they always show the countries who have, how they think they are affected. And the more red you are, the more severe is the problem. So not surprisingly, in the middle of Africa, there's a lot of problems in hunger. And also not surprisingly, Northern Europe, Northern US, things are okay. Australia, in the southern part of South America, so typically all where you have enough water, right? So everything comes somehow down to water. I'm not sure how true it is or not. You see here, India is still also put in an orange color. It's still problematic, and I think again there's probably a big difference between rural areas and city areas. So again, this is not a map coming from me. This comes from this World Food Program, what they say every year. But I would like to show you something which I think is also interesting. So this was the hunger map of 2013, and this is the hunger map of 2015. Hey, lots more green, right? The world has become a better place. Just 2 years. Just 2 years. Look at this again. Look at this here. So large parts of South America, yellow, China is yellow, and so on. Russia has this also, it's not really good. 2 years later, everything is green. Green, green, China became better, Australia, lots of more green places. The world did not become a better place. But let me tell you what they did. In this map, you were green when less than 2.5% of your population was affected by hunger. In this map, you became green if less than 5% are affected by hunger. So they have shifted the brackets. And so that why it looked like the world becomes a better place is because they just measure it differently. That is something politics is doing a lot, and unfortunately, this is not how it should be. I have written to them and I said, how can you do this? And they said, we got so much pressure from other governments that we had to do it. We got pressurized a lot to change it, and then you can see some countries did not even report their data any longer, and so that is something which where you can see how politics sometimes try to dismantle or to try to make things look better than they really are. The UNESCO has a program every few times. Every few years they have a new program. The current one is Hunger Can Be Eliminated in Our Lifetimes, and they typically have to make a new program every few years because they run out of funding in the old program, and then they have to declare that it has failed and now they need a new program, right? It's a big thing, big thing, and that is why I'm telling you this, is because if we talk about renewable resources for chemistry, we need to take that into consideration, and we need to find a way to use renewable resources for chemistry, not instead of food production, but in parallel to food production. And that is something I would like to stress here. Now, here again, a few years later, there's the Hunger Map 2020. Now the colors have changed, right? I don't know what this organization is doing, but if you can see here, I wrote to them in 2016, and you can see now they are back to the 2.5% bracket again. So you're only blue when this is the case. And interesting and very good to see. I don't know how that happened, but India is now also improved a lot. And I hope this is indeed, I think India is very hard trying to improve infrastructure. We had here this rural conclave. I heard about fantastic developments, what people are doing in order to improve development in rural areas. And so I think this is something, I was fascinated by this, and I think that is a very important task which we have. Okay, here's another interesting fact. Food loss is a major contributor to carbon dioxide emission. If food loss would be a country, then it would be the third biggest carbon dioxide emitter after China and the US, right? And so that's a big problem. And of course, we all know some of the food already, when we harvested it, is of course lost. There's very little we can do. But sometimes, and I'm embarrassed to say, especially in the country of Germany, we very often throw things out because we don't use that responsibly, we don't plan ahead. Sometimes we believe in expiration dates, and the food is still good. We don't like ugly foods, like if a potato looks like this, the grocery stores cannot sell it because people don't want it. So this is one thing, a very simple thing, where we can already do a big contribution in order to reduce carbon dioxide emission. Bioethanol, again, let me point out, it comes mostly from eatable resources, corn, potatoes, wheat. That is where we get it from. But there are a lot of efforts, what they call now second generation biomass. And that is typically what is meant, that you use not the eatable biomass for chemistry, but that you use what you call the waste materials. And so, for example, you use the straw which you produce from growing the plants, and you can see that this is going already at very good amounts. It's not at the billion tons, but it's at the million ton scale already, where this is being produced, right? And so I think this is the way to do it. And the question is, what type of chemistry can we develop from this, right? And so I told you already, the first generation of biomass to make ethanol, that uses starch. This is edible, but the idea is to use cellulose or hemicellulose, which comes from the shells of the plants, which comes from hay, which comes from straw, and also find enzymes and also find degradation ways to make glucose out of this, and then glucose we can enzymatically degrade to ethanol, right? And so that is a big effort in there. And there are already plants who do this. I'm aware of one plant in Osaka, and we actually have one plant in Straubing, which is about 30 kilometers away from Regensburg. They have a way to convert cellulose into ethanol. It's not very, very strong. They make 150,000 liters a year. This is essentially nothing, but it's a very good start to do this and to think about this. So then if you think about second generation biomass compounds, so the so-called waste, which we say, there's a lot of advertisement that one might want to use it as organocatalyst because they say it satisfies more or less all the principles of green chemicals. They are biodegradable. They can often use in water or solvent-free conditions. They're very safe, low toxicity, and so on. So there's a lot of advertisement for this. But let's talk about the reality. And I just show you will have that course on organocatalysis. Let me just show you one thing which people have tried. So they have used the chitosan, which I told you is from the shrimp shells, and they have tried to use this as an organocatalyst. And they have used this aldo reaction between the paranitrobenzaldehyde and cyclohexanone. It's one of the best aldo reactions which you can catalyze by an organocatalyst, right? And the idea is that the amino group will be able to form an enamine, and the enamine will add to the aldehyde. This is the chemistry which is behind this. And you can see what they are able to accomplish. They are able to get, with 22 more % catalyst, that is very high, 48 hours, so 22 more % catalyst. This has 5 turnovers of a catalyst which has a very high molecular weight. So the mass percentage is probably more than 100% here. It can be run in water, that's good. Room temperature of 48 hours, it makes this compound. It makes it as a mixture of stereoisomers, and there is some preference for the one over the other, right? And so I'm not sure if this is a representative example, but look what chemists can do. We can do the more or less same reaction with very small peptide catalysts. We can do this much faster at a much lower catalyst loading. We get much higher yields. We get much higher enantioselectivity. So it's again very, very important to look for applications which can really make an impact and not look at something which chemistry can compete already much better. So let's talk about bulk and big scale. So the one renewable resource which I think is very valuable is lignocellulose, because the lignocellulose comes from grass, hay, shells of corns. That's where the lignocellulose is in. And the lignocellulose has 3 major components. It has cellulose, and you can see that's about roughly 40% or so, and the cellulose, we talked about this, is glucose polymers which are equatorial, which has this equatorial connection, and so that's why we said it's very difficult to use because it makes this hydrogen bond here, and that is why it's such a hard material. The second component you have in lignocellulose is the hemicellulose. That's about there for about 30%. And the hemicellulose compares to cellulose that it's the C5 sugar. You see there's this one carbon unit is missing here. So the hemicellulose is a mixture of C5 sugars. And then one very, very big component, again also about 30%, is lignin. And lignin, you can see already, if you would have asked, and I could never answer this, if you would say, can you write down the structure of lignin, you can see this is very complicated because it's a mixture. It's a mixture of polymeric phenols, alcohols, all kinds of things. And we have it, of course, in huge quantities, but the question is, how can we make useful chemistry out of this? And so if you look at this, lignocellulose is the one component which we can produce in parallel to food production, so no starch and so on. But the question is, how can we make useful chemistry out of this, right? And so I think we have, and so if I will ask you this, what makes it so difficult to work with these materials? Why can we not use it like we use oil? Complex composition, productivity issue. Complex composition, I understand. Productivity issue, I'm not really sure. Difficult to separate.
Yeah, but you see, the good thing about lignocellulose is you make it in parallel. You grow the wheat, you grow the corn, and then you use the corn or the wheat, for the corn or the wheat, you use it for feeding. And then you use the shells, which you usually would throw away. That is what is the lignocellulose. So the thing, and that's what we have, and you're absolutely right. I think feeding the world is the first priority, but that's what I'm saying. You can do this and still produce this lignocellulose without cutting into the food production. Solubility, very important, right? Think about this. I can throw wood into water or probably whatever. If you spill in the lab dichloromethane on a wood bench, it might look a little bit ugly afterwards, but it's not dissolving, right? So solubility is very important. And biomass complexity is also very, very important issue, because I just showed you, if I go back for a second, that the lignocellulose has 3 components. But each of these components, for example, in the hemicellulose, the C5 sugars, there are lots of different stereoisomers. So you have many different sugars you have in there, and then the lignin is like a disaster, right, in terms of chemistry. So absolutely, the complex structure and also to make one type of compound out of this. And then I'm not sure if anybody has written to this. We need to consider, let me see if I have it on my next slide. How do we do chemistry from oil? We take the oil and then we put it in a steam cracker, and these steam crackers are pretty impressive. Again, I have this one from BASF, 64,000 square meters. This is half your campus. Probably not, your campus is very big. That's half of the Regensburg campus. So Regensburg, our campus is I think a little bit smaller. And they make 2 million tons just of the naphtha itself. And you see, here's why this works. Because the oil is something you can distill, you can heat, and so that's what they do is they have this in these steam crackers, and then they have different thermal areas, from cool areas to very hot areas, 350 degrees, and then the oil breaks up in the cracking, and then depending on the boiling point, you get different fractions. And so that is something you can do very efficiently. And so you have a light fraction, like a C6 fraction, which gives you gasoline. You have a heavier fraction, which gives you like C6 to C10 or so. That is what typically is being used for chemicals. You have an even heavier fraction that's used for the aircraft fuel. And then you have diesel, and then in the very end you have residues. This is what you can make, where you can make streets from, and so it's a lot thing. But the important thing is we can distill it. We can, and by fractional distillation, we can crack it. We cannot do this with wood, right? It's not working. And so there is a big problem in processing already the wood, right? And so this is why biomass is of course very interesting. I would say biomass for materials, this is probably pretty good already by making buildings. But fuels and chemicals, this is still very much underexplored. Okay, so here again, lignin, right? A complete disaster of compounds. And I just would like to show you, people have done already quite a bit more on what can be done. I would just like to show you that there have been, in all these complex structures, there have been some units identified which always look like the same. And so these are the 3 units which you have identified in this. And so especially, let's look at the first unit here, where you have an aromatic system, and it's like a diol, and this diol has a phenol in the end, right? And now the question is, can we break this down to easier parts? And so people have studied, this was a very interesting publication, people have studied this as a model compound, and you see this is exactly the same, more or less the same issue like here. So this has this phenolic part here, and then it has this benzylic alcohol. And they have looked how to do this with catalysts to degrade this. And you can see they are able to degrade this unit by making a palladium insertion into this bond here, and then eliminate carbon monoxide. This carbon goes as carbon monoxide. They are able to get the furan, and they have the phenol, and then they are able to get the toluene. So that's pretty cool. If you can do this, and you see the yield up to 73%, that's pretty good. And you see, it would make very useful compounds. It would essentially make toluene. It would make a phenol that's, again, from oil produced on a very large scale. And it would make carbon monoxide, which we use, for example, for the hydroformulations. That is pretty good. Look at the conditions. So they need an acidic additive. That is okay. Then they need 5 mole% of this iridium complex. And you see, this is a dimer. This is actually 10 mole% of iridium, right? Because the complex has 2 iridiums in there. So they need 10 mole% of iridium. Then it needs to be heated by 120 degrees for 24 to 48 hours. And this is the gold standard here. That was hailed as a major breakthrough in lignin degradation. But you can see how unattractive, how completely impossible such conditions would be to run this on any type, even on kilogram scale. It would be already a problem. And so there are indeed a lot of lignin processes, and I will not go to this in too much detail, but there is a lot of chemistry going on, and most of the thing is the way, how can we process it, right? How can we dissolve it? For example, you see here they use concentrated sulfuric acid to extract the lignin, and preferentially to the celluloses. You can also do hydroxide and again extract the lignin away from the sugars. And so quite a number of ways. The problem is, again, it's an environmental problem. Very often you do this because you have huge masses of this lignin, or of the wood fibers. You cannot just put it in a flask, right? So typically what they do very often is they put it outside on huge fields, several football fields big, and then they dump sulfuric acid on this. And that's, of course, also not good, right? So the processing is still a major problem with this. One looks at it to enzymes, and so there are a number of enzymes which can do this type of degradation, which again cleave these same bonds which I showed you with this iridium catalyst, which is doing. I'm not going into detail. There have been projects, there have been pilot plants being built, and to my understanding is it was stopped, so they were not able to really get it up to production scale. One thing you can do is pyrolysis. So essentially you heat it to very high temperature. So again, very high temperatures, very energy intensive. And then you see these diols you have here in your compound. You can start eliminating water, right? So if you, for example, take this hydrogen here and the phenol, then if you eliminate phenol, then you're getting out this phenol and you're getting such an alkene here. And so that is I think is a very promising way to degrade this by simply different types of heating. And then depending on the temperature, you can break it down all the way to either smaller chemicals, like I show you here, but if you really go up in the chemistry a lot, you can actually make almost coal out of this. It's coke, and so you can do pyrolyze it and essentially try to mimic the geothermal or the geoprocess which you have in order to make such type of compounds. So again, that is going on a lot, but it's again very highly energy intensive. I already told you you can also do it by acid type. There are lots of ways. If you look at the scripts, if you're just interested, you will have some of the references, but I will not go really into detail at this moment. Okay, let me see this. And then one thing which is of course also going on quite a bit is that you can try to use the carbon dioxide, and I think one of the big things is that you, with electrocatalysis, which we will talk about the principles, a little bit that you can reduce carbon dioxide to carbon monoxide and oxygen. And I think this is a very promising avenue in order to utilize carbon monoxide, because we know what to carbon dioxide, because we know that with carbon monoxide and hydrogen we can do hydroformylation, we can make Fischer-Tropsch synthesis to make alkanes and chemicals this way. So I believe this is a very promising way to use this. So I have given you some more issues on this, and let me just see that I'm not running. Oh, I'm still okay. So okay. So as a summary, again, lignin can actually produce already quite a number, and you see it's mostly of these phenols. They can actually produce already quite a bit by these various techniques on various scales. And so I believe there we already have quite a number of very attractive starting materials you can get by these degradation processes. The question is, on what type of big scale can we do it? And again, I give you a review here, which can be used in on very good, which you can use for looking at it further. So let me just jump to my next presentation, because I want to go a little bit more into chemistry. So I think, wait a minute, is there somebody, can you help me? We need one more presentation, because the good thing is, let me see, what we started, when did we start? 1:30, 2:30, 3:30, so we have still a little bit more time. Okay, so let's start with something more chemistry, but I need to give you my stick again. So sorry for this. So I know you gave it back to me. Now let me see. I copy it again. I don't know where I have put my other stick. Okay. Okay. There's a lecture 4 on there now. Yeah. Yeah, it's this one.
This one.
Yeah.
Just open.
Yeah, it doesn't matter. You can copy it or you can open it. Okay. So let me continue a little bit about this. We have talked about this, then the lignocellulose, and again, from this review I just showed you, it's not only the cellulose, but it also the C5 and C6 sugars. People have developed a lot of chemistry already from this, and what I will going to do is I would just like to give you a few things on one specific class of renewable resources, which I think are very useful. So the US Department of Energy, they have the compounds you see here in black, they have published and they have said these are useful platform chemicals. So platform chemical is like what we would consider oil, then we crack the oil in the naphtha fraction, and there we can make a lot of different type of chemicals out of this. And so in the Department of Energy, they thought about can we do this, what would be the important compounds in from renewable resources. And you can see they put quite a number of compounds here in black. And most of these are polyhydroxylated compounds. You can probably see where this is coming from. It's coming from sugars. And then you can also see that they already had a number of furane molecules here. And then I show you in red, this is from industry, where this author here, John LeFries from DSM company, he added a few more compounds which he thought are also very useful starting materials as renewables. And so he added some terpenes, which are in lower amounts, also of course available as hydrocarbons, ethanol, carbon monoxide, which you can get potentially from carbon dioxide, and some hydroxycarboxylic acid like malic acid, which you can also get from natural resources. And so the reason probably he added these and also some more of these furanes is that the furanes you can distill, and that makes it much more easy to use them. And so here I have already given you more or less the answer to this. So if you think about furanes, what makes them attractive as platform chemicals? And I've already told you it's you can distill them. So that is something which is relatively nice to have. As I say, I have given you very good. So some people are paying attention here, very good. They are not non-toxic. That's the interesting thing. They have been implicated, at least, that they could be able to cause cancer. On the other hand, we are eating them probably all the time, because when we have sugars and when we heat, when we prepare food, see, if you look at this, if you have sugar like glucose, this can be in the pyranose form, or it can also be present, it's in equilibrium with the furanose form, right? And if you start from the furanose form, if you start eliminating water out of this sugar, so it doesn't matter where you start, you just take out water subsequently, inevitably you will arrive at a furan molecule. And it doesn't matter of the stereochemistry here, which type of C6 sugar you had. You see, you still have the 6 atoms, the 6 carbons, 1, 2, 3, 4, 5, 6, and you will, in the end up with a furan molecule, which has, in this case, one hydroxyl group and an aldehyde left, right? You do the elimination of water over here. This gives you the aldehyde. And ultimately, the driving force is that you're making an aromatic system. So you use the aromatic driving force to do this. And now you have converted a mixture of C6 sugars into this hydroxymethylene furfural, which you can purify by distillation. So you can see what they used to do is this. If this represents a mill to grind corn, then typically what you do is you grind the corn, and then out of this you get what you can use then the corns for making bread and so on. But then the shells are very light, and they fall to the bottom and they fall out. And what people did is they made these masks in order to have some fun. So it looked like that the shells were puked out from these masks. And at that time the people represented and said, oh look, this is all waste. This is nothing we can really use. But this is exactly where the hemicellulose comes from. And now again, in parallel, you can use these shells, this grass, this hemicellulose in order to make these type of furane compounds. And again, I just show this without now going into detail, but if you're interested in, you can look at these pictures, that there are plants to make this, and there are about 300,000 tons a year of the furfural, which are produced from hemicellulose. The overwhelming majority comes from China, and then South Africa, Dominican Republic also make quite a bit. The carbon dioxide balance is a lot better here. You make about 13 kilograms per carbon dioxide per kilogram furfural. That's a lot better than in the other type of process I've shown you. And again, this is there are a number of companies, and you see some of the parameters. So if you're interested in this, you can look up more of the details later. So then the question comes, what do you do with the furanes? And so this is, again, we can make them, but the type of chemistry which is being developed so far is, I would say, is not that attractive, or it might be attractive, but it is not so useful to make all kinds of fine chemicals. So what people have done a lot is they have taken these dicarboxylic acids, and then of course they reduced the carboxylic acid compounds to aldehydes, to alcohols. You can hydrogenate this. Now you see the good part is when you produce it, you make an aromatic system that's very stable. But it's very hard to break this aromaticity again to make compounds out of this. But that is one thing what is tried to make the amines, and then you can make polyamides, you can make polymers out of it. So quite a number of chemistry. You can try to make polyesters out of this for clothes, and to rival essentially processes which we have developed from oil. And here again are some of the products which people have made from furfural, and as I said, a lot of polyesters are made, because usually this is what we can make a lot of clothes out of this. Let me show you some more things, because these are chemicals which can be done. You can reduce furfural aldehyde. You can, by a catalytic hydrogenation, you can reduce the aldehyde group to an alcohol group. That is something in the lab you would probably do with sodium borohydride or lithium aluminum hydride. But that's, of course, a hydride reaction is not very sustainable, but being able to use this as hydrogen, that is pretty good. And there are also quite a number of not precious catalysts which can do this. You see, again, it's very energy intensive. We're always coming back to the same problem, that we need a lot of energy for these type of processes, but then it allows you to reduce the aldehyde and to make it essentially methyl tetrahydrofurane out of this, right? And here are some more hydrogenation products which people can do. Then eventually you can also hydrogenate the methyl tetrahydrofurane, the methyl furane to methyl tetrahydrofurane, in order to make again compounds. We use THF as a solvent in our laboratories a lot, right? And if you think about tetrahydrofurane, typically you make this by an oil-based route. You use butadiene. You can do an oxidation and then a carbonylation in the end to make tetrahydrofurane. But the biomass route from furfural and then taking away, doing a decarbonylation chemistry will also allow you to make tetrahydrofurane as a solvent. So that's again one of the bigger, this is one of the biggest applications. The easiest way would be to make 2-methyl tetrahydrofurane. I could ask you, why do you not use 2-methyl tetrahydrofurane in the lab as a solvent? Because you use THF a lot. Now if you think about if you hydrogenate furfural, then you would have a green solvent, and then you would have 2-methyl tetrahydrofurane. And so there is a problem with this. So it's probably less miscible with water than tetrahydrofurane is, right? THF, about 8% will mix with water. Boiling point might be a little bit higher, yes. So it can be good, can be bad. But indeed, one of the big issues is the peroxide formation, right? We try these days to avoid alpha to an oxygen. The CH is very easily oxidized by oxygen, and the higher this is substituted, the more easy the peroxides form. And so on this position, this forms very easily peroxides by oxygen, right? We already have this with THF and with ethers. If you let it stand too long in the sun, then you might form peroxides, but with the 2-methyl THF, it's even a bigger problem. Okay, so I have some more examples. All I wanted to tell you here is that most of the furfuryl alcohol we produce from furfural, so the reduction product, most of this goes into polymer chemistry, into resins. Right? Okay, so here's again an interesting reaction. You can work through the mechanism. If you start from the furfuryl alcohol, under acidic conditions, you can make this livolenic acid. And this livolenic acid, again, is a very big compound which people like to use as renewable resources. And if you look at this, how this is being rearranged, if you look through the mechanism, this really goes by a protonation of the furfuryl alcohol, water elimination. You can form such an intermediate. And if this adds water on the other side, so on this side, you form this intermediate, which then actually can break down. And if I rewrite the enolate as a carbonyl group, and if you now start adding more water to this bond, you can form a water adduct. And after elimination, ultimately, you will form a carboxylic acid here from this moiety, and you make this livolenic acid. And so that is a very good process. Again, it's being done on very large scale, and produced. And so there was a very interesting project, again, which came from the DSM company, and they thought, can we use livolenic acid? Can we make adipic acid out of this? Huge compound. 2.5 million tons of adipic acid are produced annually. And so I will ask you in the next question why that is. Why are people making this so much? You can buy it in India. You can buy it for 80 rupees per kilogram. So why is this so important? And normally it's made from oil. But the question DSM was asking, can we make it from livolenic acid? And you will see that they use some very modern chemistry for this. They were proposing to reduce this carbonyl group to the alcohol and then do an intramolecular esterification, which would form this valerolactone. And then they would reopen this and they would form such acrylates. I showed this to you in the next slide a little bit again, how they think that this type of reaction occurs. And then the proposal was to do a carbonylation with palladium, carbon monoxide addition onto this carbon in the presence of methanol, which would give you this methyl ester here. And if you would hydrolyze this, you would get the adipic acid. So you start from essentially from C5, which you can get from the furfural, and then by doing one carbonylation with carbon monoxide, you would be able to arrive ultimately at adipic acid. And I show you in a moment what they all did and what they all what this was, how this was accomplished or how this was not accomplished. But why is adipic acid so important? This is indeed, why do we produce millions of tons of adipic acid every year? And I show you a picture here. This is a picture which I think was taken 1944. And just after World War II ended. No idea, it's not coming up. Let me see. Ah, okay. Okay, now it's coming up. Okay, it's used as a preservative in food. No, it's not. What we are using in food when you go there is benzoic acid. That is being used a lot as a food preservative, and that is approved for this kind. It's not true. It's also not used as a biofuel, so nobody likes this. And it's important in the military sector. That's indeed true. And you see here this line coming up, being said. That was shortly after World War II ended, or maybe it was just ended, maybe it was 1945. And you can see many people, and especially women, have lined up to get not adipic acid, but the product you get out of adipic acid, and that is nylon. And so in the Second World War, you needed nylon for parachutes instead of silk, which was much more expensive and not as robust. So you needed it for parachutes, and you needed it so much that you could not buy any stockings or any other things for the daily use out of nylon, because it went all in the military, all in the military sector. But then after the World War was over, people would line up to buy again, especially nylon stockings again. So it's a very important issue. So let me show you a few of the reactions they did. So as I have shown you already 2 slides before, what they are doing is they are ring opening with acid this butyrolactone, and you see if you bring in a hydroxyl group here and then eliminate water, you will ultimately get a double bond here. And the double bond can be on different positions because it can migrate, right? If you add with water on this position, you can do the water elimination to this side. And I didn't want to do this. Right, so the idea is you do this opening, and then if you do subsequently the water addition, can occur to either side, and then the double bond can migrate further because you're making an alpha-beta unsaturated carbonyl compound. So you get all these type of compounds and these olefins, and this is what DSM then thought, okay, now maybe we can do a palladium catalyzed carbonylation out of this, out of the double bond, right? And so if you just draw this, if you just draw it like this, then the idea would have been to have palladium carbon monoxide essentially do like a hydroformylation, only that you will have oxygen on the side as well. And so if I if I draw this like this, you can get the insertion into the bond here, and get such an acyl complex. And if this eliminates water again, then you can get the product out of this. And so that was a palladium catalyzed coupling reaction they developed, and they actually, without going too much into detail, you can see what industry is typically doing is they evaluate a lot of parameters like temperature, carbon monoxide pressure, more catalyst, and quite a bit more, and they were able to develop this, and you see here in the developing process up to 98% selectivity to go directly from the mixture of the alkenes, because the double bonds would isomerize, and ultimately the carbonylation on this position is sterically most favored, so it would do this, and they would be able to get this compound out of this. And interestingly enough, also they used heterogeneous catalysts, but they again used the nanoparticle versions of these type of catalysts rather than using molecular catalysts. Right? Here's another type of chemistry which was developed, and that is from the hydroxymethylene furane. Again, if you try to hydrogenate this, hydrogenate everything and cleave the furane molecules, you can make the corresponding C6 dialcohol. And then if you do an oxidation and form you might be able to form a lactone. And if you treat this with ammonia, you might form caprolactam. And again, this is something industry has been trying to do. And epsilon caprolactam, again, is important for the polyamide type chemistry. So again, just to give you an idea what can be done is they have developed hydrogenation chemistry, and that would typically do exactly what you think. You would hydrogenate the double bonds. You would come to this compound. But then they also found that in 4%, they can hydrogenate the carbon-oxygen single bonds here. So 4%, this is of course not very good. But then they were able to optimize this process further beyond this. And let me show you this. Again, very quickly without going into detail, they've been actually able to optimize the hydrogenation of the tetrahydrofurane to this dialcohol, ultimately opening this up and making 3 different alcohols, making this alcohol in a very selective way, and subsequently do another cyclization and hydrogenation to get this alcohol, which they can transform in the lactone, which I just showed you before. Let me jump over this a little, because I think this is something we do not really need so much. Okay. All right. Okay, it looks like I'm a little bit faster than I intended to, but nevertheless, I suggest we go and take a break right now, because I don't really want to go too much into these details, and I think we rather do the tutorial than afterwards. So let's have a small break now, and then we continue a little later with a small tutorial.
but in an applied context with some chemistry where catalysis is involved. And this is actually an interesting or famous example. This is an example which comes out from the groups of Eric Jacobsen and from Japanese scientist Katsuki. And it is the catalytic epoxidation of alkenes to form such epoxides. Very important in as building blocks for synthetic chemistry, and we will see one application to an HIV protease inhibitor where this reaction is actually being used. This is a reaction which is being catalyzed by manganese. We talked earlier about abundant metals, so this is an example which I could have mentioned at that point already, where manganese is actually really a catalyst which can do this. And you can see it's a chiral catalyst. It's one of the so-called silane complexes which you synthesize from a right. So they're very easy. They can be very easily synthesized from such aldehydes. And the amine and then we have the second aldehyde over here. And the second phenol. And again the groups here. So very easy. It's essentially one step from this. This is salicylaldehyde. If you think about aspirin, aspirin is a phenol with a carboxylic acid next to it, right? So that's a very common building block. And so here they use the phenol and an aldehyde next to it. That's very readily available. So in one step, you can generate these type of ligands with a manganese catalyst. Manganese, then you can coordinate manganese in there. That's manganese 3. And you can make such a complex which is able to epoxidize alkenes in an enantioselective way. And there are two variants. Look at this. There's the Jacobsen variant and there's the Katsuki variant. American scientists, Japanese scientists, and look at this. They're using pretty much the same catalyst. They're using a manganese, and the Katsuki, when he synthesized it, he didn't use manganese 3 chloride for the compensation. He used the PF6 salt. So that's why I have drawn it here as a cationic with a non-coordinating anion. In the Jacobsen case, the chloride is still bind, but this is still a manganese 3. And then you can also see it's a very similar ligand backbone here. So Katsuki is using the diphenyl Jacobsen was using the cyclohexyldiamine, right? But I think you would agree that this is very, very similar in the structure. Look at the years when this publication came out. 1991. This cannot be a coincidence, right? That suddenly two of these very similar, very similar things came out. And let me see if I can get it here. Oops, okay. Discard, let me just give you a new, let me just get a new slide here. I hate PCs, okay. Okay, just so that I have something to draw. So indeed, it was not an accident that both of these publications, and the one from the US, the other one from Japan, came side to side. If you think about the accomplishments of Barry Sharpless. Barry Sharpless is now a twofold Nobel Prize winner, right? In 2001, Barry Sharpless got the Nobel Prize for asymmetric oxidation. And can anyone tell me which reactions he has developed, which gave him the Nobel Prize? Sorry? The Sharpless epoxidation is an epoxidation which epoxidizes what? Alkenes, but a special class of alkenes. Allylic alcohols, very good. The allylic alcohol, and you see now here, so he did, the one reaction he did is the allylic alcohols epoxidation, where he was able to take an allylic alcohol, let me draw it like this, and he was using a titanium 4 precursor titanium tetraisopropoxide, and then he is using tartrate as a chiral ligand and then he's needing an oxidant, which could be typically triarylamine N oxide or so. And right, and the idea is here that, and that's the reason why he needed, I think he used T-butoxide, right, as well. You see that I'm not. I think this is actually what he's using. I was mixing this up. Not sure how I get this out, because we go to the second reaction just a moment. So this is the stoichiometric oxidant. And the reason he needs to do this on the allylic alcohols is because the allylic alcohol would coordinate on the titanium, right? He needs the coordination, and then some kind of a peroxide complex is being formed, which then eventually will deliver the oxygen to the allylic alcohol, right? And so you need the coordination. This is why the Sharpless epoxidation only works with allylic alcohols. So this is the one reaction which he got cited for. There's a second reaction which is attributed to Sharpless. Does anyone know which one this is? Because he got in general asymmetric oxidation. He did not win the Nobel Prize for asymmetric epoxidation of allylic alcohols. There's a second, and then you might even argue there's a third reaction which he developed. Does anyone know what else? Exactly, the dihydroxylation, the asymmetric dihydroxylation. Let's take, for example, one like this, and then he developed with essentially osmium tetroxide and chiral ligands, and the chiral ligands are kind of complicated. These are Chinka alkaloids, but this is the reaction, and then here, see, this is what I was mixing up. Here he's using these N oxides as a stoichiometric oxidant.
and then, for example, he was able to develop the dihydroxylation. So that was Sharpless. And then the third reaction along these lines is that he developed also, when you use osmium tetroxide, but if you use this in the presence of a tosylamine, then instead of getting a dihydroxylation, he could get an aminohydroxylation. So then he could transfer also this reaction. So these were the three reactions which Sharpless developed. And if you look at this, the allylic epoxidation, this is an epoxidation reaction. This is also an epoxidation reaction. So that's in a way very similar. The big difference in the so-called Jacobson-Katsky reaction, hello, is that it works with unactivated alkenes. In this reaction, you do not need the allylic alcohol. Okay, so why did this come out both at the same time? Japan and US scientists. This came because Jacobson and Katsky were both postdocs in the Sharpless lab. Right, in the end of the 80s, I think 85 and later, they were quite some time. So they were both in the same group. And they were, of course, must have been a lot of talk going on about epoxidation chemistry, how they can develop this better. And so I'm sure that this reaction was around. And people thought about this in the Sharpless group. And the one thing which I like always to say about Barry Sharpless is a very generous person. And so probably this idea was circulating around in his group, but he didn't try to take charge of it. He said to probably both Jacobson and Katsky, guys, why don't you go and develop this? And then they went back and started their independent career, Eric Jacobson in the US, Katsky in Japan, but they came up with more or less the same, they realized the same idea pretty much at the same time. Now let's look what they did, because there are differences to this. And that's what I would like to ask you, and then I can have a question where you can give your opinion. I would like you to analyze the two epoxidation protocols they have developed. And let's assume that they have more or less the same catalyst. Katsky had an additional stereocenter put in here, which I think to my idea did not really bring a lot. They have a difference here in the backbone, but again, conceptually it's the same. So I think it's a relatively similar catalyst design. It's the same metal oxidation. But look what they do here. So Jacobson is using as a stoichiometric oxidant sodium hypochlorite. And you all know how we make this, right? This is bleach. It costs nothing, right? This is essentially chlorine plus water, or chlorine plus sodium hydroxide. And then this makes this, right? So this is what he's using as an oxidant. Katsky, this is the oxidant of Katsky, iodobenzene, right? A hypervalent iodo compound. And so he's using this. Then you can see both use dichloromethane. This is a reaction done at room temperature. This is a little bit lower, 4 degrees. I would say this is still water ice baths. Reaction times are a little bit different. And Katsuki is using a additive still. He's using a pyridine N oxide. And so he is stating in his protocol that the reason he's using this is apparently it scavenges something, it stabilizes the epoxides for opening, right? So again, I'm not really sure what this is the case. Look at this, again, also very similar. Both use 2 mole percent of a catalyst. Both have a very similar yield. What I show you here is 2 different substrates. You see that this substrate in Jacobson gives you 98% EE. Katsuki achieves 83% EE. It might not be the same type of substrate. You see, this gem dimethyl group probably brings you a lot of steric interactions. And so I would argue, I couldn't find it. I checked the Jacobson publications. He never used this naphthalene derivative Katsuki used. So it's not easy to compare this one-to-one. So then let's talk about, and then you see they're using 2, he has different substrate, 2 to 15 mole percent, 2 mole percent of the catalyst. So if you would have to choose between the 2 protocols, which one would you choose? So now you're the CEO of a company, and so your 2 co-workers come to you, and the one says, I'm using Jacobson protocol, sodium hypochlorite, gives you good reactivity. I have to run the reaction at 4 degrees, and then I can do it high EE, and that's of course very important. And then the other coworker comes and says, I'm using iodozobenzene, and I run this at room temperature. Which one would you like better? Can show this again to you. So here are the protocols. Sodium hypochlorite is the oxidant. Iodobenzene is the oxidant. Both use methylene chloride, right? So there's not really a big difference. And let me tell you, I know both of them, or I knew both of them. I would say Katsuki died a couple of years ago, very young, a relatively young age, the age of 60. But I knew both of them, and when I would talk to either of them and say, so which protocol is better, they would say mine. So that's not really objective, but maybe we can find out about the reason why everybody made a case. So you don't want to decide here. As a CEO later in your company, you have to decide. So you have to tell your one coworker, we do it your way, and then the other one is disappointed. But that's life. You have to make a decision. So in this case, it's easy. It's only top or bottom. So only the question, Jacobson protocol or Katsuki protocol. Is it all working? Is that maybe the problem? That nobody wants to make a decision? So you need a new code, right? You know this? 201294. It's working for me. It should work for you. It's not showing. Ah, okay. Oh, so our American friend is winning, right? 89% to 90% to 10%. Okay. So you guys like this. And I think you're absolutely right. Everybody likes this, right? And I I went to Katsuki once, I met him once, and I said, why do you do this with iodobenzene, right? Because this is, I think, the one thing we don't like here. Let's go, I think I have this again. Right? This is the one thing which we think is probably not good, because with the what seems to be very attractive is, this is your stoichiometric oxidant, sodium hypochlorite. What is the byproduct you're making if you use this? What's the byproduct? You transfer the oxygen, you make the epoxide, and then what is the byproduct? Huh? Everybody who wrote earlier that in your dreams you want to become a teacher, the one thing you need to learn is to speak with a loud voice. Very important. So what's the byproduct? You use sodium hypochlorite, oxygen goes into the product, makes the epoxide, and then sodium chloride. Hey, this couldn't be much better, right? Sodium chloride is the byproduct here. Hey, that's pretty cool. And we know, of course, we use sodium chloride in food and everything. If you have done such an epoxidation and then you isolate the sodium chloride, would you put it onto your egg and then eat it? Probably not, right? That is waste. That's the one thing you need to realize. It's very inexpensive, it's very non-toxic, but it is waste. You cannot use it for anything. And so that is probably landfill, because recycling sodium chloride is not so easy. It's a salt. When you make salts, we have not talked about this, but normally in industrial processes you avoid salts. In the Katsuki protocol, what is your byproduct here? Iodobenzene, right? So you're making iodobenzene. Can you recycle this? And where do you want to recycle it to? You want to bring it back here. And how do you do this? Sorry? MCBA? Yeah, you see, you work too much in the lab. MCBA is absolutely right. Metachloropherbenzoic acid. But from an industrial point of view, there's a better way. What else could you use as an oxidant? Hydrogen peroxide. So you use iodobenzene and hydrogen peroxide to bring it back. And so this is the interesting point here. So ultimately, the Katsuki epoxidation works with this hydrogen peroxide, and the iodobenzene is just the mediator. It's a stoichiometric mediator. Later on, we will see also, especially in the electrocatalysis, you would like to have catalytic mediators, right? You would like to have the iodobenzene and the hydrogen peroxide in the same pot and your manganese catalyst, and then you would like to see that the hydrogen peroxide is oxidizing the iodobenzene, and then you would like to see that the iodobenzene gets converted by the manganese catalyst. I don't think they have been able to accomplish this. They could not do it in the one pot, but they could, after the reaction, treat the iodobenzene with hydrogen peroxide, get the reagent back with the sodium chloride, as inexpensive as it is. But the problem is to discard it, to dispose it. It's something which then the disposal becomes expensive. And with a lot of organic waste also, you can burn it. Sodium chloride you cannot burn. This is waste which does not go anywhere, right? And so that's an interesting case. And I remember when Katsuki told me this, he said, you know, Japanese industry is using my process. And I say, of course, because Japanese industry is very loyal. And he said, no, that's not the reason. That reason is the recycling aspect here. And so that's something I think you always should be aware of this. And so I'm not sure that Katsuki has not published too much on this. If I would compare the substrates with, if I would compare the substrates, if he could get EE values like you have here, 98 EE, and then because here you see here he has 83% EE. One very important aspect in asymmetric catalysis is, especially if you think about industrial applications, is the question, should you use an asymmetric catalyst, or should you make the product racemic and then separate? And separation sometimes can be very easy. For example, you make a racemic carboxylic acid or so, then you can take a chiroamine and do a recrystallization. And the point for this is, what industry will tell you is, we use you see, if you do asymmetric catalysis, like such an epoxidation, you can simply run with hydrogen peroxide. You don't need a chiral catalyst for this. But if you want to use a chiral catalyst, it's normally more elaborate. You need to make the chiral catalyst. Very often you need more specialized reaction conditions, lower temperatures, and so it's more effort to do it. And then the point is, if your reaction will not give you 98% EE, sometimes even more, because if you make a drug, you're not allowed to have the other enantiomer present. If you make a chiral drug, you can only have one enantiomer in your drug. So let's say you have 83% EE in the lab, you would be very happy about this, because 83% EE is roughly 90 to 10. That's already a very good result. But it's not sufficient. Industry would have, if you want to have this in a drug synthesis, you need to separate. And for industry, very often, it doesn't matter if it's 50-50 or 90-10. You still have to separate. So then they very often say, let's do 50-50. We separate. And very often, we are able to recycle the unwanted enantiomer back into the process, right? So that's also why you do not see so many asymmetric reactions in industry. We do this a lot in the lab. We are very, very happy with this. But unless you can get it to enantiopurity, it's always the question, is there a benefit in doing this? I show you now a benefit, because this Jacobson protocol, there was a, let me see this, I have made just some more. So this epoxidation was being used for making this amino alcohol. And this is a very important amino alcohol, because this was in a commercial protease inhibitor, one of the most successful protease inhibitors, which was developed by Merck, Sharp, and Dohme. And in order to make this one, they needed this amino alcohol. And so, could be already my first and general question. I have not put this up, but how would you synthesize this? Do you have any spontaneous idea how to do this? I give you the idea they had is that they wanted to make this from the indene, and the way they wanted to make this is they wanted to use this epoxide with this Jacobson epoxidation, which we have just seen. And they tested this in the lab, and it worked brilliantly. It worked fantastic. Essentially, one enantiomer, good reaction time, good catalyst loading. They were so happy about this reaction, that they wanted to use this. Now tell me, where is this challenge? How do you go? Okay, I can ask this, but I have this so that everybody can answer. How do you go from here to here? So you see you have the epoxide, and now you want to make the amino alcohol. Sure. Sure. Then I just cannot move around. Okay. That's fine. Fine. But it's not working. It's not working. Oh, now it's working. I think it's working. It's working. I just need to be close enough. Oh, I get it. Okay, so look again at this epoxide, right? So first of all, we all know we can open, let's start with something simpler here. We can open epoxide by nucleophiles, right? Nevertheless, put a ring on here, a simple ring. And then if we do this...
Now it's working.
It's working? Yeah. Great. Okay, let me put this off. So if we do this epoxide opening, what type of mechanism is this? Sorry? It's an SN, and it's probably an SN2 reaction, right? We can discuss in a moment if it could also go by SN1, but it's probably SN2. And you see, this is what you guys wrote down with cis stereochemistry and stereochemistry. It gives you the trans product, but they wanted the cis. All right, so that's already the first problem here. And then you guys also mentioned the question of the nucleophile, right? Ammonia would have been maybe one nucleophile. It's, you know, it's a gas, aqueous solution. Maybe you could use if you analyze this, maybe you could use an amine where you can deprotect the group again. So benzylamine, open, and then by catalytic hydrogenation, deprotect the benzylamine. We talked about the green principles. One of the green principles was no derivatization. Here we would have first a protecting group on and then a protecting group off. Someone wrote azide. Azide is a great nucleophile for making amines, because once you have the azide, then very easily, by palladium hydrogenation, for example, you can convert an azide into an amine. But why does industry not like this? Industry will be very, very nervous about this, running this on 100 kilogram scale. What's the problem?
One step more.
Sorry?
One step more.
Yeah, it's one step more, okay, but it's great steps. Azide, a fantastic nucleophile. And then the hydrogenation, it's like you can do it actually in the same pot. You add the azide, you let it react for an hour or so, you add the balloon with hydrogen and palladium, it's great. But what does industry not like about azides? Sorry? Say it out so that I can hear it. It's exactly the right answer. It's explosive. Exactly. It's explosive. And I will, on one of the later days, I will go with you through a case study how they made Tamiflu, which was the big medicine against the SARS virus in 2005. And I will show you the academic synthesis, which uses lots of azides. Then I show you we will discuss then the so-called academic synthesis they did in industry, in the pilot lab or so, where they would make a few 20, 30, 50 grams. And then I show you what process chemistry did. And process chemistry, the only concern they had was, how do we get rid of the azide nucleophile? And that is something as unfortunate as I say. It's great, it's a fantastic reagent, but on large scale, it's unacceptable in industry. And so that's an interesting question. But still, in all these cases, this doesn't help us, right? It doesn't help us. And now look at this epoxide I've drawn up here. There's even another problem. So you come in with your nucleophile, but this time my epoxide is unsymmetric, right? So let's call this A and let's call this B. So if it goes the A way, then my nucleophile will have attacked here. But if it goes the B way, then my nucleophile will have attacked here. And so which one is what are they needing? They're needing the A case, right? So they need the amino group on the benzylic position. So this was desired. No, this was actually not desired, but the desired regiochemistry. And this would be the undesired regiochemistry. And in addition, cis is desired and not trans. So is this now the end of your project? Can you, if you look at these two opening pathways, could you say which one maybe is preferred? Is there one which is preferred, or are both equal? What would be your take on this? And ideally, you would like to see that the A path is preferred, right? It's not the B path you would like to have. So what do you probably maybe could do in order to prefer the A path? I will draw this up here again. And we would like to see the attack here. You guys all said SN2 mechanism. Is there an alternative to the SN2 mechanism in such epoxide openings? When we have a nucleophilic substitution, this is a nucleophilic substitution, right? That's what you said, SN2. What is the alternative to SN2? Sorry? SN1. This is all simple chemistry here. That's a good thing. SN1 would be, so if you bring this to an SN1 type reaction, let's say we go there with a strong acid. I draw this here again. So we protonate this. Which bond, carbon-oxygen bond, would you think would preferentially open? The benzylic position, right? This bond this here is a benzylic position. So if this bond breaks, you would end up with this cation. So that's okay, already good news, right? Because at least now you could make an argument that your regiochemistry is okay. Now you come in with your nucleophile. Let's say you do the azide or you do the amine. You see there's already a slight problem. Amine and acid might be not compatible, but if you adjust it carefully in the pH, like pH 6, 5 or so, you would get away with having acid and base next to each other. How confident would you be that your nucleophile would attack from the same site now? So what would you expect now from the nucleophile? Would you expect selectivity? If a nucleophile comes from the outside, would you expect, you see, it has to come from, it has to attack from the same side like the, has to attack from the same side like the hydroxyl group, right? You think that would work? Probably would not work, right? The hydroxyl group, first of all, the hydroxyl group is bigger than the hydrogen, not a lot, but it's a little bigger, right? So if I would make a prediction, I would say the nucleophile will come opposite from the hydroxyl group. And then I might convince myself, because I really want to see that at least some of that cis alcohol is being formed, I would convince myself and say, but maybe the hydroxyl group is small, so I might also get some of the desired one. So at least I would get a mixture, right? So that's okay. So you go to your boss and say, I think I have a plan, but I will get a mixture. Is that okay? And then your boss will say, no, that's not okay. We don't want mixture, right? We want, because mixture, you probably, it's both is an amino alcohol. You probably would have to do chromatography, and right? And we are talking about an intermediate. They produce this on ton scale, right? This was in the height of AIDS when they needed really these HIV proteins. There was this, you are too young for this, but when AIDS came up in the 80s, there was we had all the feeling when it came up in the beginning that it would eradicate the world. And then it turned out that with protection and so on, the Western world pretty fast had it under control. Then it looked like it was more or less only a problem in Africa, but a huge problem. It's still today a huge problem. But because there was such a fear in the 80s that this might affect the whole world, all the big pharma went into AIDS research, and they made such drugs. And then the one thing I like very much is we saw in the Western world pretty much we get it under control, but it was not under control in Africa. And the companies could also not really make a lot of money, but what they did is, because you know that AIDS therapy, you're not using just one drug, you use a combination, you use a mixture. And so all the pharma companies came together, they produced, essentially everybody had a compound, a drug. They realized that if the three drugs are taken together, it's better because the resistances are not so much. And so what they did is they gave the medicine, they stopped all the AIDS research, but they gave the medicine to Africa for free. And I thought that was a pretty good way to do it. Okay, so as I say, we are now at the point that regiochemistry is under control, stereochemistry not so great. So here comes the solution, and I think this is really nice. Does anyone know the nucleophile we are going to use? Don't know if anyone knows this, but I think it's a beautiful classic. You don't know. You're using acetonitrile. Hey, that's interesting, right? Making with acetonitrile in amine, have you heard about this? Probably not, right? But in this case, and you will see this case is special because we need the alcohol. So you use acetonitrile as a nucleophile. Acetonitrile, we use it as a solvent very often, but acetonitrile is a nitrogen nucleophile. So it will attack this point here. Is there any selectivity? Will it come from up? Will it come from below? What's your feeling? It's not selective, right? We would think it's probably not selective, and you're absolutely right. It is not selective. But let me draw it first without the stereochemistry. So I leave this up because this zero center is controlled. Okay, so this is the intermediate you would make. Does this look like a happy intermediate to you? Probably not, right? It has the positive nitrogen. Looks like it can nowhere go. The only way this could go is back. Does anyone see what else it could do rather than reacting back? How could it somehow stabilize or get rid of that positive charge we have? Anyone have an idea? Look at this intermediate which is drawn here. You can what?
Using water.
Water, yeah. That's probably what you could do. But if you can use water, what else could you use? Water, so what you're saying is water, the hydroxyl group would add on the carbonyl group, on the C of the nitrile. So a hydroxy group could add on the nitrile. So what else, if you don't have water, who else could add? Sorry? This OH here, right? So this could add here. And now look what you're doing. Let's count the atoms. 1, 2, 3, 4, 5. 2 5-membered rings on each other. If you have a situation, let me draw it here. If you have a situation like this, you can build a model. This is only stable if it's a cis annulation. If the 2 hydrogens will be trans, you cannot close the ring. It is too strained. It can only 2 5-membered rings together will only work in a cis junction. So if this goes from the opposite side, it will not close. And all it will do is it will react back. But if it has attacked from the same side, so let me now draw it from the same side. This is the intermediate where you now can have generated this. So now you see what you have done. The nitrogen and the oxygen are now on the same side. How you need it. And now a simple acid hydrolysis will give you the amino alcohol, and essentially what you get out of this here is acetic acid, right, as the byproduct from the hydrolysis. So that's, I think it's really beautiful, right? It's really fantastic. Now you go to your boss and say, you know, I have the solution. You get a nice bonus because this was a major problem to solve, because they found out that the trans compound is completely inactive in this. So it really, this cis interaction was absolute key. Very unfortunately that they stopped that type of research, or actually even the synthesis is stopped today, because for the longest time we could write to Merck and say, could we get 50 grams of this amino alcohol for free, and they would give it to you because they would produce it on ton scale. And it's not, at least from Europe, at least we are not able to do this any longer. Yeah. Okay, so this is the When did we start? Sangeeta, help me. When did we start? We started. Sorry? Yeah, I know. I forgot when we started. So 1 hour is over, right? Okay, good. Because I told you in the end, I would like to tell you a little bit about the postdoc and PhD applications. Okay. Here I show you another example. This is a biased example. I will talk about this also a little bit tomorrow on the furans. This is the very famous Piancatelli rearrangement. And in the Piancatelli rearrangement, you again take one of these hydroxymethylene furan and you convert it into a hydroxycyclopentanone. And so if you look at this reaction, we can think about atom economy here. And we can also think about then the reaction conditions. And so this was a reaction published. This was published actually the first time already in the 80s. Here's another publication from 1997. And you can see what they do is they do this in water. And they use 125 grams and 3.7 liters of water. They use a base additive, they use phosphate as a additive, and then they adjust it, it's a buffer solution. They adjust this to pH 4.1, and then you heat it for 40 hours at 99 degrees Celsius, and you get out 50% of the product. And interestingly, if you read this publication, they say it's a dark red oil, okay, and you get about 50% of that, of this this reaction. And so the alternative to this is you do this not at 99 degrees, or that's essentially 100. I don't know how they came up with 99 degrees in their publication. Now let's do it much hotter. Let's do it at 240 degrees. But then the reaction only takes 4 hours, and you see here's the little apparatus. What you do is only this apparatus has the 240 degrees, and you pump it through. Similar to what I told you earlier on the aluminum oxide type catalyst, is that you don't need to heat your whole reaction mixture. You just need to heat essentially your reactor, and then you pass through your reaction. You pass through your reaction mixture, and so the exposure time is very short, and you don't heat the whole solution. You only heat always part of the solution, right? And so when you do it by this, again, you can do it in water. You do it 460 milliliters. So you see in this case, it's 1/10 of the scale, 12.5 grams to 125 grams. And you can, again, you do it at around the same pH, pH of 4, that was optimal. And you use about half a liter of solvent. You use water acetone, and in this case you use a little bit toluene as a co-solvent to keep your reactor clean, to wash out some polymer which might be forming here. And so in this case, again, you get 87% yield. In this case, the purity was measured, so there was no purity measured here. And so if you would compare these two processes, one at 100 degrees, one at 240 degrees, probably could ask you again, which protocol would you use? There's very big solidarity here in this room. It's very good, right? Because let me go back. You might have noticed that this protocol is from my group. So it's very nice of you that you all stick to me. And I have to talk to the two persons who want to the above protocol. I have to have a serious chat with them. Because, it's getting less. Very good. The good part is I don't know who answered this, so you're safe, right? I mean, in a way, you have, of course, absolutely right. And the first way is here you need an apparatus, and here you need simply your flask. Let me tell you, we did this together with a company who made this nice apparatus. Our first flow reactor was a tube from a GC oven, an empty tube, which we put in the GC oven because there we would be able to get the 240 degrees. And so we had simply an oven, a GC tube, and then we pumped our solutions through this GC oven. So that was a micro reactor for poor people. And we were poor, academics are always poor, so that's how we did it. And then when we saw that this is actually a pretty good process, we did it together with industry. And here's an interesting question. If you analyze the reaction, you see here the yield is only 53%. If you think about this, why this is, you are heating in the batch process, you're heating for a long time your product. You're heating for a long time your product in acid. What do you think could happen with the product? Do you think that is happy if you heat it with acid? Does anyone see what maybe a follow-up reaction could be? Very simple. You know from first year organic chemistry. Sorry? Water could be eliminated, exactly. Water could be eliminated, and not only this, that is something probably you cannot know, or you only know if you read about this. You would form cyclopentadienone. This is not stable. This polymerizes. So that's the end of it. If you have this side reaction, you cannot even use the cyclopentadienone any longer. That's gone. And so normally, when you think, how can I improve on a process, usually you would say, oh, I need milder reaction conditions. Lower temperature, maybe better catalyst or so, lower. But one very good strategy, indeed, is to have more forcing reaction conditions, 240 degrees, but expose your compound only very, very short time. You see, it's only 1 minute in the reactor. Expose it a very short time, and then it's out of the reactor, and you can cool it down, right? And so that is a very important message, which I would like to do, that very often you think high temperature might be very, very harsh, but especially if you are in this situation, that was also what we had earlier with the aluminum oxide catalyst. So you had like this, in this BASF protocol I showed you, you had the aluminum oxide silver catalyst. This was 500 degrees, but your compound would not see the 500 degrees very long because it just gets funneled over the hot surface, and then before it knows it's already gone, it has reacted, and then it's getting cooled off again. So very often, although it sounds like very high temperature conditions, can be actually a milder way to do chemistry than if you heat something for a long time in a batch reactor. And we actually reproduced it. The compound you get out here is not very pure, and you could see it. They say it's a dark red oil. If it's completely purified, it's actually a colorless solid. And so that is something where we appreciated the idea that high temperature can actually be actually good for the reaction. I didn't ask you yet about the atom economy, I guess. Can you see why this is that a good reaction in terms of atom economy? Should I show this to you again? So here's the reaction again. I'll give you a moment to count atoms here. That's because that's what you would have to do. Let me see. No. Anyone has an idea about the atom economy? I'm not sure if I see anyone getting out a calculator here. I hope you don't need a calculator. Here's the reaction. Nobody is happy with the atom, or is it not working again? Let me see this. Now. Okay. I'm the one with the 0%, by the way. I have just tell you that. Near 90%, somebody says 100%, 78%, 80%. You all agree it's probably pretty high. And you probably could not count this so much, but it's 100%. The molecular formula, the sum formula on the left is the exact same like on the right. So that's pretty cool, right? That is a really interesting process, which we like, because it's a renewable resource which makes the cyclopentanone in 100% economy, atom economic reaction. But then, what do you think is the worst step in this protocol, the most energy intensive step? And I show this again to you, how we do it. So it doesn't matter which protocol you take, and don't also worry the yield. So it's aqueous, it's an aqueous acid buffer, and that's simply how you do the reaction. And what do you think is the worst step in this type of reaction from an energy point of view? And we actually calculated this. 95 or 90% of the energy goes in what of this process? Yeah, I give this to you back. Okay. So here is the reaction, right? And it's also, I have also written the workup, which we also thought is nice in our case, because we work up we do washing with an ether. In the other protocol, they did the washing with dichloromethane, but they probably could also have done it with something else. In 1997, there was not so much concern about chlorinated solvent as it is probably today. And so they heat for 40 hours, 99 degrees. We heat for 4 hours, 240 degrees. You need to be fair. Our scale is 10 times smaller, so we probably 4 hours. So probably in order to do the same amount, we also have to heat 40 hours for 240 degrees. Only a smaller batch. Let's see. What's the most energy intensive step? Okay. Now, the reaction works as it is. I'm just talking about the overall reaction, maybe not like intermediates you have, and you're right. It's a de-aromatization reaction, so some of the activation barriers is high, but just look at the overall process. We take the left compound, we convert it into hydroxycyclopentanone, we heat it, and then we extract it, and then we evaporate the aqueous solution. What do you think is the most energy intensive process here? More than 90% of the energy. And it's true for both cases. Oxidation by potassium dihydrogen. There is no oxidation. It's a rearrangement, 100% atom economy. The potassium diphosphate, phosphoric acid, is only there to adjust the pH, to keep the pH constant. It's like a buffer. The purification, what part of purification do you mean? Protonation dehydration sequence, but the reaction goes all the way.
But you're very right on this. It's in the purification. Because what do we have to do? This is a water-soluble product. We run the reaction in water. We need to get the product out of the water. And we cannot do it by extraction because it is so water-soluble that if we extract it with ether, they extract it with dichloromethane, it stays in the aqueous layer. So you need to distill the water off. And this is where 80 or almost 85 or 90%, I forgot what it is, we calculated this. This is where all the energy goes. And as I said again, as we talked about this, water as a green solvent has typically the problem that it's very difficult to get rid of it. And so that's really where all the energy in this case goes to. Industry, if industry is doing the mass balance or the energy balance, it's a little bit better. So we do this in the moment with industry, this process. They have different types. They're not distilling water off. They have apparatus where they essentially rotate, and then in the vacuum they are much more efficient than distillation because they have a higher surface. But still, the major energy intake is the workup here, and it's not the reaction. It's neither the 99 degrees they use here or our 240 degrees is to get the product out of the water. So that's the problem. Here's another famous synthesis, I told you, vitamin A synthesis by BASF. And that's what they do 3,800 tons a year. And they just reopened their plant, a new plant, I think, in 2021 or so. It's a pretty new. So let's have a look how they do it, right? So they start from this compound, which we talked about this before. What they do is they add acetylene here to the carbonyl group. I couldn't find in order to do the acetylene addition, you need to deprotonate the acetylene, right? I couldn't find what base they're using for this. Acetylene, pKa of about 20, so you probably get away with some base, but very often still LDA or magnesium type, linear type chemistry is being used. So I don't know, I couldn't find it, right? So they add acetylene to the carbonyl group. Then they do a hydrogenation of the triple bond to the double bond. See, they're using a palladium catalyst, which is poisoned, typical poison in a catalyst, which only attacks triple bonds and is not attacking double bonds. Why is the triple bond more reactive than a double bond? Can anyone tell me this in a hydrogenation? I'm sure everybody learns about this. Poisonous catalyst goes for the triple bond, doesn't go for the double bond. So that must mean the triple bond is more reactive. Sorry? It's linear. But the double bond with normal palladium, it's also reacting. So, but it's linear, so you mean it's more accessible? I'm not sure if I would take this as the reason. Because it's also true when you have two substituents on the double bond. In this case, it's a terminal double bond. I don't think it's a real reason. But let us recall something. A CC bond, CC single bond, what's the bond strength? How strong is a CC single bond? Anyone? I'm not advocating to memorize such things, but a few things are good to know. So how strong is the CC bond is good to know. Roughly 154. I think what you're thinking about is the bond length. 154 picometers, 1.454 angstrom is a CC single bond, the length. But how strong is it? Roughly? Anyone here? Few bond strengths to know is good to learn, because if you look from a product, from starting material to the product, very often you can analyze if a reaction is thermodynamically favored or not if you compare how do you
which bonds are you exchanging. So for example, you can immediately say that a Diels-Alder reaction see, for example, if you have a Diels-Alder reaction, I can immediately say that the product should be thermodynamically favored because I'm exchanging 2 pi bonds for 2 sigma bonds, right? I'm making 2 new sigma bonds and I'm giving away 2 pi bonds. And the sigma bond, the CC sigma bond, is worth roughly 100 kcal per mole. You guys are all young. For you, it's probably 400 kjoule per mole, right? Are you calculating in kcal or in kjoule? Huh? Kjoule. Here's the point. I like to calculate in kcal, and this is not because I'm old. This is because, at least my generation, we learned to calculate in our heads. And we could calculate between 1 and 100 much better than between 1 and 400. So I'm really good in calculating up to like 10 times 10 is 100, right? That's what we had to memorize. If you stay in kcal per mole, you can, everything you need to memorize, you stay in the area between 1 and 100. If you calculate in kjoule per mole, suddenly you are between 1 and 400. I know in my head that I need to multiply by 4. I know the kcal number and I know how to get to kjoule, right? And you again can see it because nobody could tell me really how strong a CC single bond is, right? And for me it's easy, it's around 100. That's it. I can memorize this much better than 400, or I think it's even 430 because it's not exactly times 4, right? So at least you can do it as you want, but a few type of things, of bond lengths, strengths is good to know, right? Rotation around a single bond between 3 and maybe 10 kcal. Chair flip of a cyclohexane is 10 kcal. Aromatic stabilization energy, 35 kcal. So it's all okay. If you want times 4, it's okay. These are a few of the numbers you need to know. Pi bond in an alkene, so not the CC, but the pi bond, roughly 80 kcal per mole. And the second pi bond in the acetylene, 60 kcal per mole. And this is the reason. The second pi bond is much weaker than the first pi bond. So this is why the second pi bond you can preferentially hit without hitting then the alkene bond. And it's about 20 kcal per mole. So it's right. And so sterics might be accessibility. I will not take this away from you, but I think this is really the argument here you have here. Right? So they do the hydrogenation. And now very interesting, as their key step, they're using, now they make a phosphoylate. So the phosphine is doing a SN2 prime reaction. So the phosphor has a nucleophile, they do it in the presence of an acid, so this gets protonated. And of course the phosphine will attack in the SN2 prime, and it will not attack here, right? Because you cannot do an SN2 reaction on the tertiary center, right? So it's all okay. So it makes this one, and then they do the Wittig reaction with this molecule, and I've shown you how they make this molecule here as well on the left side. Very, very nice. Acetylene, again, needs to get deprotonated, is reacted twice with formaldehyde. It makes this compound. And then, at the same time, they make butadiene, they do an epoxidation, and again, you can see it's not a molecular catalyst. It's again this idea oxygen silver makes this. Then they are able to combine these two molecules by doing the epoxide opening, coming up to here. Hydroformylation, we talked about this briefly already, is able to install the aldehyde group here on the center. Elimination, they're getting this compound they need over here. And then they do the Wittig reaction in order to make the vitamin A acetate. And as I say, this is done on 3,800 tons a year. If you consider all of these reactions, from an atom economy and from a waste point of view, which one would you think is the worst step in this chemistry? It's the last question for today. After this, I tell you something about PhD applications. So I show this to you again. Here's the whole sequence, lots of different chemistry steps. And I give you a hint, the worst reaction in here is a reaction a Nobel Prize was given for before you were born. I was already alive. I think it was 1977. No answers yet? Now guys, everybody contributes. It's the last thing you need to do today. Second step. What the heck is second step? Tell me the reaction. Tell me the reaction. Second step, is this a hydrogenation here? Multi-step reaction. Yes, of course, it's multi-step. But I think the guys from the BASF would argue, hey, we are pretty good. Acetylene, hydrogenation, here we add formaldehyde to an alkyne, and then we do epoxidation with oxygen. I think they will argue. They will argue and say that's all pretty cool. But there's one step maybe which is not so cool. And then we need to discuss if it is still cool for BASF. And the BASF is the only there, and in the handout you can look at this from this morning. There were three more vitamin A syntheses, but BASF is the only one who's doing it this way. Okay, everybody is happy with this. I already will call up a new page here. Yes. Okay. Let me give a new slide here. I give you one more chance. Presence of metal, that's probably, as I said, right? I was not really sure to find out what the basis is they are using. So they must probably use a type of metal base to make the metal acetylide. Making the phosphorus ylide. It's probably not so much the making it, but it's the Wittig reaction in general. Right? Let's think about this. The Wittig reaction, Nobel Prize. What do we do in the Wittig reaction? In the Wittig reaction, let's take it in the most easiest way. We have a carbonyl compound. This is the most unfavorable one which you can think of. We have the Wittig ylide. And then we're making triphenylphosphine oxide. So look at this. We put a CH2 group in the product, plus 14. And triphenylphosphine oxide, if I'm not completely mistaken, has a molecular weight of 273. That's almost 20 times as much. You're making 20 times the waste triphenylphosphine oxide from what you transfer into the product. In the process of the BASF, it's a little bit better because you see they're transferring all this. So this is what? C6, 7, 8, 9, 10, 11, 12, 13, 14. So they're probably having 150 grams, but they still, with each Wittig molecule they're producing one equivalent of triphenylphosphine oxide. And so the Wittig reaction is probably one of the most inefficient, from the point of atom economy, one of the most inefficient ways you can do. Now think about this, 3,800 tons. This means that you're making twice as much, 7,500 tons of triphenylphosphine oxide. This would fill much more than the room here, right? And you would do this every year. What a disaster. But BASF said, we can live with this. Why can BASF live with this? And this is the big advantage of a company who essentially makes everything. And they have so many other processes. So what they did is they say, okay, wait a minute. We can take the triphenylphosphine oxide and we treat it with this compound, and we are making the dichloro compound and carbon dioxide. So they're converting the triphenylphosphine to the trichloro compound, and then they're reducing the dichlorophosphine compound, they're reducing this aluminum to aluminum trichloride and triphenylphosphine. So now they have back the triphenylphosphine at the expense that they're now having aluminum trichloride produced. But what do they need the aluminum trichloride for? Do you remember from, sorry? As loose acid, for which reaction specifically, where you need it a lot? You need it for, Friedel-Crafts, exactly. And this is still, from an atom economy point, it's a very bad reaction, but you cannot really do it differently. And at least this is how they produce the aluminum trichloride. They need to do Friedel-Crafts chemistry out of this here. So this is pretty cool, right? Is there a problem with this reaction sequence? Is that something you would think, oh, next Wittig reaction I do the same because I want to recycle and I have a Friedel-Crafts alkylation to run as well, then I make the aluminum chloride. What do you think is problematic here in this sequence? And the BASF is one of the few companies, if not the only company, who is allowed to run this reaction on ton scale. And we're talking thousands of tons. Did I write this clear enough? I think I did. I still have a little bit problem with this pen. There is a very toxic reagent involved in this sequence. Yeah, which one? This one. That's phosgene. Exactly. This is phosgene. Very, very toxic and a gas. If there is an accident with phosgene, everybody in the area of I don't know how big it is will die, right? So phosgene, because if you inhale it, makes hydrogen chloride and you're dead immediately. And so BASF is one of the very few companies who is allowed to work with phosgene on megaton scale. And let me tell you how it was. So I have actually visited it, and it's pretty impressive. So here's the street in the BASF area. And so they had already a phosgene plant, small one, phosgene. They had it here, but the vitamin A fabric was here. And this street was maybe, I don't know, maybe 10 meters wide, 10 meter wide. And then, so this was. So all they would have had to do is they would have to build like a pipe, right, where goes the phosphine, and then they can pump it to the vitamin A and they'll recycle this. They were not allowed to do it.
they had to build a new phosgene plant directly next to the vitamin A brand, because even making a pipe there, you were not allowed to do it. So they had to do the phosgene plant connected directly with your vitamin A plant, and so get it together. And I visited once. It's pretty amazing. You see the phosgene in the reactors, and it's behind glass walls which are this thick. And you know, if anything happens with these glass walls, you will not be able to get out of the room fast enough. So it's pretty impressive. But this is what a great big company can do. They can really, and as I say, you are all chemists. We need to learn how to use also even hazardous reagents. And you see, this is very bad in the green principles we just said, because this is using a super, super, super toxic reagent. But if it's done in a good way, and then you see if it's reacting, it makes carbon dioxide. That is a pretty good way to do this. Okay, so this is so much for the few things I wanted to discuss with you guys. And since you guys are all interested about postdoc and PhDs, let me tell you very briefly 10 minutes of this tutorial. That's okay, right? You can do this. Let me tell you a little bit about this. Applying for PhD or postdoc abroad, do's and don't do's, right? I had in my career, I probably had 25, maybe even 30 PhD students from India. A really large number. And it's fantastic to have. I mean, you guys are so talented, dedicated. One really feels that you really like chemistry, and you're just wonderful co-workers. And if I could, I would take twice as many students as I can. And the problem is, it's very difficult. It's funding is very expensive. The best road to success is typically a DAAD fellowship. And because one of the things is from the university funding, you would have to teach. Teaching is still, at least in the undergraduate classes, it's in German. So it's very, very difficult to get independent or to get funding for this. And so nevertheless, it's still, and as I say, I would like to take many, many more students from India than I can take. Just to give you an idea, I probably get 3 applications per week. And you can easily do the math. I probably get 150 applications a year. I try to answer them all, but even this sometimes slips me because it simply gets too much. So let me just give you, and again, it's not a clear way that you are successful, but let me give, from my perspective, let me give you a few points which I look at, and I look at if I should very briefly just say, I'm sorry, I cannot take any more students, or if I should at least explore the possibility if this would be a good candidate. And so there are the 3 aspects, I think. Is you need to file a good application, and I tell you a few things about this. It needs to be the right timing, and that is sometimes very, very unfortunate that I'm getting an application from a good candidate, just the DAD has one deadline a year. And so sometimes you send me an application 2 days after the deadline. If you would have sent it to me 4 weeks earlier, it would be a very different matter, because then I would have said, let's try to file an application. So timing is important. And of course, where can we apply for funding? So again, I would say there's no reason that the quality of the Indian students is really fantastic. I like the knowledge of chemistry. I like the creativity. The skills in the lab is very good. You guys are very, very, very good in the, and I also like the personality. It's really nice to talk, you interact. I like the motivation a lot that you really like chemistry. And that's probably the most important things, that you have a passion for chemistry, that it's not just a job for you, that you really like chemistry, like this. I see sometimes my co-workers sitting in the kitchen and maybe drinking a beer or having some sweets or so, and then they still discuss their projects, right? And I think this is, of course, fantastic, really being interested in this, right? And
this is also for me, this is the first message I would like to give you. You need to like what you do, because only then you will do it well. And so if you would like to apply for PhD position or postdoc, and you just write to essentially everyone which you can find on the pages and file applications just in the hopes to get a position, that's not a good strategy. Because even if you would get it, because maybe there's some money or so around, if you don't like the project, then you're not happy with this, and you're supposed to do the project a year or maybe 2, and you really need to like it. And so don't get into the situation that only because you want to go abroad or so that you do something which is not really which you're not really excited about, right? So that's very, 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 very important. And I have no problem with also our students. Some students tell me and say, I don't like organic chemistry, I want to do inorganic chemistry or physical chemistry. Okay, everybody is different, right? But it's important that when you do something, you really need to like it, otherwise it will not work. Okay. So, as I say, this is a small part of chemist I had with me. And also the one thing I would like to point out, and some of you already had one of my students, Victor, here coming from Regensburg. I think it's equally important that we do it both ways, right? So it should not be only that you guys come to us, it should also be that we come to you. And I had a number of my students coming, and I'm very happy that you always have so much hospitality for our students, right? And so also I have, I think, more than 50 publications together with my Indian co-workers. So also very, very good. And so here's some more. Okay, so what am I looking for a postdoc position, right? Again, genuine interest in the research we are doing. And so unfortunately, very often in your applications are some standard sentences I read in essentially every sentence, right? And so the other thing I look in that you have matching or complementary skills. It's okay for me if you come and say, I want to do photocatalysis, and I've never done photocatalysis in my life, but I've done a lot of transition metal catalysis or whatever. You don't need to be a perfect fit, right? That's okay for me, but it needs to be matching, complementary skills, and you should clearly address it in the application, right? Don't pretend and say, I have read every paper on photocatalysis and I know I can do it, and then probably if you look closer, you cannot do it. Writing skills is very, very important, because for me, if I look for an applicant, I immediately ask myself, can this person write an application for a DAD fellowship? Can this person write a publication, at least a reasonable publication draft, right? Can this person be, when you write me about your research summary, are the drawings nice? Are the schemes nice, right? This might sound very, very minimal for me, but for me it's always the question, if I get a draft, and if I have to correct everything, and maybe even in the end I have to do the drawings myself, then that's something I cannot do, right? So when you prepare your application, when you prepare your research summary, you really need to put effort in this and make it nice. And there are now also so many of these KI tools where you can correct spelling, correct grammar. You need to use it, right? Because this is something I think I'm not the only one who is about this. Communication skills also is important. A lot of people of you speak very softly, almost a little bit shy. No need to do this, right? You have to have a loud voice, you have to speak with confidence, you have also because what happens typically is when you're interested in a candidate, you do a Zoom interview, you need to present this with confidence and so on. So don't be, I know that sometimes, and especially in the beginning of a career, something very hard, but communication, of course, is very, very important. Theoretical knowledge, you typically all have very well, experimental skills, and a good team player, of course, an international and diverse group, and that goes to everything. I have different cultures, genders, religions in my group, and this needs to be done, right? One targeted application is better than 100 serial applications, and for me, I typically can see very quickly if that application was sent to me, or if you have sent an application, the same application, to 15 other groups, right? And that is something you need to make this clear. You need to make clear that you are really interested in joining this specific group you are writing to, and not that it is a genuine and general application you are writing, right? And on the other hand, what I already said, only apply to groups you have a real interest to work with. You don't want to get stuck in a group where you don't like the projects, you don't like the chemistry, just because it's abroad, right? That is not a good strategy. You need to, at least in Germany, for a PhD program and also for a postdoc, you don't apply to the school. You apply to the specific group leader. And that is something you need to do. And it starts with some things which you need to be aware of. If you write, address this, dear professor, typically at the minimum write the name of the person. Write dear Oliver Reiser, dear Professor Reiser, also it's all okay. But dear professor immediately tells me that application probably went to 20 other groups as well, right? Because this goes for everything, right? Dear prof, that's also not probably good. Respected sir, this is very difficult, and I must say I understand that we have a cultural difference here. At least in Germany, sir, madam are words we are not using, right? If you address someone as sir, and I know you guys do this very automatically, right? You say yes sir, no sir, and so on. It's something we don't do in Germany. And I think we don't do it in the US also, unless you have incredible respect. Sir maybe goes in the UK, but then you have to earn this title. Not everybody is a sir, or not everybody is a madam. You get this from the Queen, you get this title awarded. So I know that it's much more common in your language, but you need to avoid it, right? And you it doesn't work very well. And I might say it especially does not work very well if you apply to a group, dear sir or respected sir, but the group leader is a female. This is my wife. She is also a professor in molecular biology at the University of Salzburg. And I cannot tell you how often she got upset when she gets these applications and said, the guy or the applicant didn't even look at my website, right? Didn't even know who I am, right? And so these applications, the delete button is hit essentially immediately, right? Dear Madam Sir is also not very good because it shows you it's a general application. It's not directed to the person where you want to go, right? So this is probably the better way, right? You write the name, you address the name, and there you can, it doesn't matter if you take the last name, the full name, whatever. This is all okay, right? That's the one thing to do, right? The other thing is, if you apply, my recommendation would be don't apply to more than one faculty member at the same place. Or, if for some reason, we have a center of photocatalysis. So in Regensburg, just about anybody is doing photocatalysis. If you apply, let's say, to me and at the same time to my colleague, Professor Koenig, that's okay. But then you should address it in your cover letter. You should say, I'm applying to you, la la la, because I'm interested in photocatalysis. I have also applied for the same reason to the group of Professor Koenig. Because the one thing is you need to understand is colleagues talk. And so if I go to lunch, I say, oh, I have a really great candidate who has applied to me. And then my colleague says, oh, what's the name? I got a great application as well. And then you see immediately in the question, should I take effort now, or should my colleague take effort in this? You need to be open about this, right? And then at this point you say you are open, you say I applied to your colleague as well. Then we can both discuss it. We can say, oh, this is a better match for you, better match for you. Should you answer, should I answer, or so, right? You need to be open about this because we find out anyhow. That's the that's the thing, right? And so, as I say, this is typically what you then be open about this is you say you would like to work in this area, and I'm aware Regensburg has a center, so this actually shows already that you looked a little bit closer of what we can offer, and then you bring open that you have a parallel application, right? Because as I say, we talk over a beer or whatever, and then we don't want to get the feeling that we are competing for the same candidates. So, okay, strong command of English. Touchy touchy topic in India, because more or less you feel that you grow up with English. For me, it's a foreign language, second language, but you grow up and you have a lot of English around you. I have TV maybe, and you speak sometimes. I have Indians in my lab who can only talk English to each other because one of them might not speak Hindi, and then they come from different areas, so the dialect is not the same, but they can only talk in English, right? And so that's the interesting thing. The one country in the world which speaks English is the USA, so population-wise, but the number 2 is already India. But there is very often a problem with the Indian English, and that is and there are very typical mistakes: wrong use of articles, wrong tenses, wrong phrasing sometimes, and that's why I'm saying you need to check your applications with these KI tools and grammar tools and spelling check tools. But you also should make a conscientious effort to learn to speak, to present in good English. And as I say, it's more touchy because you guys think you all grow up already with English, but it's not really so much the case. And that when I asked you earlier and said what do you like to do in your free time, a lot of you wrote reading books and watching movies. That's a great thing. The way I watch movies and I read books is very often I also read it for the language. I like to read papers from good American English authors in chemistry, but I'm not only reading it because I enjoy the chemistry. I also try to understand how they write it, how do they pose it. And it's very unfair sometimes, but I have been also at the conference here last week, and the chemistry which was presented from a lot of the Indian PIs was fantastic. But it was very often published in a good journal, but only a secondary journal. And the reason for that is because very often the presentation is not very good. We have some American colleagues, if they give talks, you think you want to, after the talk, you want to run to them and give them money and say, can I become part of your enterprise? I want to give you, do you sell stock options, right? The chemistry is very often not any better than yours chemistry, but the selling is really great. And that is something we will never achieve like the people from the US or UK where it's really their native language, but you need to be aware that that is a skill you should work on. So in my opinion, besides being a great scientist, the second skill you need to work on is English. Writing, presentation, very important. Right? Yeah, so that's what we always say, like the Hindi English also for this one. Okay, so as I say, you need to avoid spelling mistakes. This is like an application I have recently. Grammar mistakes, but you see here postdoctoral, the P is missing, characterization, that's misspelled. Here also I am capable, the I is wrong, and things like this. Very easy to catch, but I cannot tell you how often I get applications like this, right? And I wonder, did this person never read their own application? And so usually, this is for me the end to consider an application, because that's exactly what I think. If I get this for an application for someone who wants a job, how is it then in the end if this person is supposed to write a report or say, please publish my paper, please publish my work, right? Then I wonder, do I have to do all the work myself in the writing area, right? You also need to avoid meaningless flattery, right? You say, I am fascinated by your work since many years. I mean, that's something I simply do not believe, right? You're not old enough to be fascinated by my work for this. It was always my dream to work under your supervision. That's hollow. That's really hollow, right? And also do not go down the road of pity, right? Please help me to pursue my dreams. You guys need to be self-conscientious. You are good scientists. You have good accomplishments. You need to acknowledge that we are all getting more applications than we can handle. Okay, so we cannot, and very often you will get a negative response. Very often, unfortunately, you will get no response, right? But be self-confident in what you can offer, and don't say, oh, please take me because I need to pursue my dreams, right? So this doesn't help you. State your qualities, be confident about these, and make it clear why you would like to work in this group, right? You see, here, if I get a sentence like this, I would like to continue working in the area of sustainable chemistry. Having experienced metal catalysis, I like your approach to use furans as non-edible resources and would like to contribute to this topic. Apparently, this person has read, not just find out I work in catalysis, but really reads a little bit more about this. And then make clear how you can contribute, either the expertise matches or you have complementary expertise. This is all okay. I very recently got an application, a very well written application from someone who wants to do degradation of polyfluorinated polymers. And I thought, how the heck? I'm not doing this, but the application was really written so well, and also there was a project outline that I thought I need to pursue this. And then we talked on the Zoom, and we found out that, hey, he wants to do a bioanalytic degradation of polymers, but the methodology he wants to do, we might be able to apply it also for synthesis. And now we are filing a Humboldt application from two completely different areas, but it was a great match, and so that's why I do not look necessarily for the same expertise. It can be complementary, and sometimes this makes an even stronger application, right? And you need to explain this briefly and in a credible way. I have read all your papers. It's also something I read a lot. I would be very impressed about this, because if you take 10 minutes per paper, this will probably take you 60 hours, right, at least, so to do this. And then also what you very often do, right? I have gone through your webpage and your recent publications, such as, and then this is something I know you can get this by copy paste. And you see here, even worse, here you see the font is changing. So I know that this was copy paste, right? So I don't even need to think about this. Here this is taken directly from an application, and then you see here the font is changing. So clearly this person has done copy paste and so on. This is completely meaningless, and you need to say this, right? It will be much better you focus on one, right? I have reason on photocatalysis is what I also got on the photocatalysis synthesis. And I would like to expand my knowledge getting into this area. And now you give me an idea what you could maybe do. This, of course, takes a lot of effort. And I understand if you write 30 applications and you get only maybe once an answer, if you give every time somebody an idea, that takes a lot of effort. But on the other hand, let me tell you this. If this is a really good idea, I have not thought about this, I'm kind of a dilemma. Because I might want to do it, but I cannot steal your idea in this application, right? So if I say, hey, this is a pretty good idea, I should have thought about this, I should have done this, I would be very hesitant then to write to this person and say, sorry, I cannot take you, but I think your idea is great, we are going to do it, right? So you see, you put someone into a dilemma, in a positive dilemma, that there is an obligation that this person has to answer, and maybe say, I cannot take you, but I like your idea very much. And that is very close to a paper which we have done. We might pursue it, and then maybe we get in contact again if it works and we include you or whatsoever, right? But this is, in such an approach, you have a much better chance to get a response, right? Because you immediately in this application contribute. And that's why I said earlier, just from this degradation of these perfluorinated polymers, I thought this is completely out of my area, but I saw the mechanism how that person wants to do it, and I thought, hey, this is something we might be able to use in our chemistry, right? And so then the contact started. That's also very, it's a very good thing. It shows me that you looked at the paper and you come up with an idea, and as I say, I'm in the trouble to do this. Here's another type of applications I had, right? This is something usually also somebody told me what type of compounds they have all done. And I'm not really sure I was so much interested in this, but what I see here is that all these compounds, everything is drawn with different sizes and so on. Then in some case, the labels do not stick, labels are different. See here, the bond is not right. This clearly shows me this person will not write a good paper draft, right? It's unattractive. The graphics are unattractive, right? You see here it's even different, right? So here it's the reaction formula. This is the product which makes, and these are apparently the substituents which are hanging somewhere here. This is the R1 substituent, right? Don't do it this way. Even if you would have just given me the one equation and you don't need to show me all the examples, but make that look nice, right? Let me give me the feeling that you will write an application for a fellowship or later on a paper where the graphics are pleasing. And I see this more and more, and I have actually in a moment, I have 2 Indian PhD students who are so brilliant in this and making graphics. You open up the paper and you say, you cannot reject it because the graphics are so beautiful that you need to accept this paper, even if the chemistry is maybe not so good, right? Don't underestimate appearance, right? The chemistry, of course, has to be good as well, but the appearance, nowadays, the standards get higher and higher and higher. If you look at great papers from great authors, look at the Macmillan papers, wonderful chemistry, no doubt, but look how beautiful it is presented, right? And that is something definitely to do, right? This was much better. Research summary, don't give me all the examples, give me a drawing, but you see how nice this drawing is. Clear drawings, and this way, this looked very nice, right? Timing your application. There is little opportunity to fund postdocs or PhD students on university money. This is very expensive. Teaching obligation is included. That typically has to be in German. This will not work so easily. In some cases it works, but it does not always work. So you need to look for opportunities for fellowships. And in order to do this, you need to plan ahead. And you need to plan ahead, well, if you start your postdoctoral stay, you need to plan ahead a year in advance. PhD, probably also half a year, but you need to keep the deadlines for organizations in mind. So DAD, one deadline every year, and that's October. If you apply 2 days after that deadline, then apparently you're 2 days too late, and that has a much worse chance to get this, right? And so again, this is also very often you write and say, if there's any international fellowship, kindly let me know. You need to research that yourself. You cannot expect that you will file an application and then the person says, oh, this is so great, now I'm looking for a fellowship, right? At least find out what you have done. The DAAD has a database, and there you can give your education level, from which country you are coming, and it will give you fellowships, not only the DAAD fellowships, but it will give you other fellowships as well. You need to research this, and you cannot expect that the person who is doing this yourself. And again, if you file an application to me and you say, you can say, I would be happy if you have funding for me for a PhD fellowship, for a PhD position. But in addition, when you write, I will also be interested in applying for a DAD fellowship, and I know that the deadline is in 2 months from now, maybe we could do this together. Very different, right? Because I see that this person has also initiative to get their own funding, and that is also very, very important and to do this. And I had it in also in the other way around. I had good applications, so I wrote back and says, would you apply for a DAD fellowship? And that person would write back and say, no, it would be better if you would finance me. Not a good strategy, right? You at least always say, well, I would be happy, and sometimes I had very good applications, and then I had the possibility to do the funding for a year or so, and then the fellowship come on. But you need to show initiatives. It doesn't go by itself, right? Okay, so that's what I'm saying. The DAD has a website, and you give your the field you're working, you give your status, you give your country of origin, you say in which field you are, and then you get quite a number of ideas. This is already pretty good. For the postdocs, the one thing is the Humboldt Foundation. The Humboldt Foundation is extremely competitive, and especially from applicants from India. I think they're getting 1,000 a year, and they fund less than 100, so very, very competitive. They have no deadlines, this is the good thing, but you need to time it well. And the one thing Humboldt looks probably most for are the publications. And so you need to have a number of publications, and you need to have them as first authors, and also probably in very good journals. So again, what I said earlier, I think your chemistry is great. I'm also reviewing sometimes PhD theses for Indian institutions from candidates, and I have written in a number of my reviews, I said, you know, the chemistry is really good. Why did it appear in such a journal, right? And it was like, I'm not saying any names here, but it was a journal which was good, but which was not excellent. And you need to strive for this. And I had like some of my students, especially the students from China, they come to you and say, you're not publishing my paper in any journal which not has at least an impact factor of 5. And then you say, but I would like to send it here. And then they come to you and say, what do I need to do more? What should I do in order that we get it to the next level? Sometimes the students might say, I just get it published no matter what. But you need to look for that ambition and discuss with your supervisor. Sometimes the supervisor will say, I don't think we can get it there. Let's move to the next project. I had all these cases myself. But sometimes I'm in the situation that I say, you know, that's a really nice story. We should have 3 or 4 more examples in this area. And then the student says, oh no, I would really like to publish. It's okay if we go to this journal. Or if you say, of course I do more examples, can we then submit it to Angewandte or so, right? You need to develop that ambition. Because especially if you want to do a postdoc, especially with Humboldt or some otherwise, they look very, 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 very much for this. And also, you can only apply to Humboldt, but your host, if you apply to someone who says, let's file a Humboldt application together, will tell you this. You cannot write manuscripts in preparation. At the minimum, they have to be submitted. You cannot try. Sometimes I get also applications, and then there are 3 publications, and then there are 10 more manuscripts in preparation. That is not working, right? So you really need to strive for this. But Humboldt still is a good thing to try. But again, it's very difficult, very competitive to do this. And then there's the European Union. That is also not a bad thing. They only have 1 deadline a year. It's typically in September. And again, it become very, very, very competitive. And also, it's in a way, and there your host, your group will have to help you. Also, you have to describe a lot of non-scientific things, and that makes it very difficult. Success rate might be only around 10-15%, but still, you have to buy the lottery ticket if you want to win, right? It will not work if you don't buy the ticket. So again, that's something which I would highly recommend. The one thing I find is underestimated is every European project has to publish, it's by mandatory, has to publish new job offers, PhD or postdoc position on a website, which is called EURAccess. And you can search it. You can search it also by profession and so on. And you should look into this, because sometimes I had it myself that we had European projects, and European project means also that non-Europeans can apply for this. And sometimes we would not get so great applications. And at the same time, I got then suddenly directed applications to me from Indian fellows. And all I could say is, go through this UXS, and then there's a where you have to apply for these. Go through this portal, and then we could do something. So it's a very good source, and especially, and that's typically, you have to look at the deadline, but these Marie Curie programs typically are granted in the beginning of a year, and then they start in April. So typically in the beginning of each year, a lot of these new programs are granted, and then these offers for PhD and postdoc positions apply. So that's something I can highly recommend. Very often, again, unfortunate, you get an answer and that says you are accepted, but only, but I can only take you if you get a fellowship, right? That's very often a dilemma, because this means if you don't get the fellowship, you cannot join the group. But in this case, you need to make a decision, and the decision can be manifold. You can politely deny and say and keep applying. You can say, I do it, and then secretly apply, still keep applying and looking for other positions. That's very bad. This has also happened to me once. The moment the PI finds out about this, they will reject you right away. So if you want to do this, you need to be open about this. You need to say, I would still very much join your group, but if it's under the conditions that I need to get a fellowship, please understand, I will further apply, and I will inform you immediately if something changes. And sometimes, if I write an acceptance like this, I say, I can accept you, but only if you have a fellowship. I very often write right away and say, I completely understand if you need to, if you apply to other positions in parallel, just please keep me informed the moment your situation changes, you get accepted, you want to take a different job. It's perfectly okay. But the one thing which is really important is you need to be open about this. You cannot do this in secrecy, right? And then if you get accepted under the conditions to get a research fellowship, then do your best to write a really good proposal. And your host will help you, but you need to make a good draft, good starting point, right? And the thing is, if you write a good proposal, this might be helping you later on as well, right? You might, first of all, you might get a good position, but it might give you an idea for projects, something maybe you can use later on, and that might be a good thing. And also very often, if you get such a fellowship, for example, from DAD or Humboldt, it's not just for the fellowship itself and you come for a year or 2 years to that institution. You become an alumni. And so this will stay with you all your life. Like Humboldt, you can come back to Germany every 3 years for 3 months. The DAD alumni have also a project that after a while you can always come back for short visits. So it's really worthwhile, even though the chances might be 10, 15, 20%, it's a very good effort, it's a very good investment. If it works out, you have a lot of benefits besides the research day. If it doesn't work out, you have at least try, right? And so again, proposals, it's the same thing. Once I see them, proposals, similar to the applications, spaces are missing, things are wrong. Again, check this with tools that you make this good, right? Already here, there was a proposal, already in the title there was a spelling mistake, right? Spelling mistake, Word would have found. And so don't do this. Really take the time, write the proposal before you want to send a draft, sleep over a night, read it the next morning again, use some of the tools to get this going, right? And I use a lot of these tools. There's a spelling check, there's Grammarly.com, they have a free version, and it gives you pretty good ideas where they would say not everything is okay what it suggests, but at least obvious spelling mistakes it finds, or it finds if there's a space missing. Right here also there are lots of spaces. I was wondering if this person, if the space button was broken on the computer, right? What was going on, right? And the one thing which there might be a personal thing for me, which drives me crazy, is I'm getting a proposal. I made a good friend reading it, making suggestions, and you can see here also in this proposal it took me quite a while, and at least for me, correcting proposals takes me a long time, because I think about the sentences, I think about the way it is phrased, but I think also if the chemistry makes sense, and so typically, to give you an idea, one page takes me 1 hour. And so if you send me a 6-page proposal or so, it takes me 6 hours to go through this. And then I have it very often, I send it back and say, you need to do this. And I say, I made some corrections, but I also made some comments and say, you need to improve this, you need to improve this. And then sometimes I'm very impressed. I'm getting the next day, I'm getting the corrected version, and the person says, no, I've corrected everything. Can we file it now? Very often they have just accepted my changes, right? This is not, you need to take the time in this, and then based on the comments and corrections you get to get it right, because otherwise everybody gets really upset to have spent time, and then the person you send it back and has not really tried to improve on the proposal, but just has accepted the things you have said. Okay, so takes effort, but with talent and passion to be successful. Here's a pretty old picture of my group. You see, we have carnival once a week. I think once a year. I think you have something similar, right? You have that festival where you spray each other with paints and so on. So we have a festival where we disguise ourselves, right? And so you can see this was going on here. You can see the clear cultural differences. So these were my German students, and they were all somehow disguised. And you see here, for example, you see one of the Indian students, no disguise. So you thought that's probably not a good idea to get into this culture, right? So we have here's some more. We do this every year, and it comes out of this. And again, as I say, I have a lot of Indian co-workers. So here's Santosh Bagheera, who's trying to get a faculty position in the moment in India, and maybe some of you know him. And so I've been always very, very happy with the Indian students. As I say, if I could, I would take twice, 3 times, many times more, and I simply don't have the possibility. But I wish you all the best, and maybe the one or the other thing I said today is maybe helpful for your applications. So thank you very much, and best of luck.